Okay. All right. So very good evening all. So before starting the session, actually some of the students requested to change the session timing instead of from 5 to 9 to 5:30 to 9:30 because they are having a college issue, right? So shall we schedule the session from tomorrow? Actually, I'm speaking. Shall we continue the session from tomorrow onwards, 5:30 to 9:30? Is it okay? Now, actually, the some students are having the college schedule, so they are having a genuine issue. So then morning session, how can we listen to college going? Okay. Some are some students are saying that sir it is okay. Some are saying that sir no, continue with the same schedule. Please consider or please first try to understand their problem because they are having the college I think till 4:30 or 5 they are having the college timing, and after that they will be reaching to their home, and so it is very difficult for them to join the session at 5. Okay. Yes, if anyone want to say something, please raise your hand. Hardly within a 5 minutes we are going to close this issue. Yes, Vikrant, do you want to say something?
Hello.
Yes, please. Yes, you are audible. Please go ahead. Vikrant, you are audible. Please go ahead. Yes, Jayesh.
Sir, how many classes are left for power electronics?
For power electronics, till Friday we'll be finishing it. But it is not the issue like for power electronics.
So that would be remaining the same schedule for further subjects.
Yeah. For all the remaining means evening sessions, the schedule will be like 5:30 to 9:30. If we finalize it as a 5:30 to 9:30, then only. Morning sessions. Okay.
So 9:30 actually gets very late for the.
Yeah. I do understand.
Yes, sir. Yes.
Aki Reddy saying sir 5:30 to 9. No, 5:30 to 9. Reducing the 30 minutes is not possible. Minimum we need to keep for 4 hours.
Sir, how can we listen morning session, sir?
Your voice is breaking, Mahesh.
Sir, morning we are going to colleges, sir. We are unable to listen morning session classes, sir.
You are unable to listen morning session also?
Yes, sir. We are going to colleges, sir. How can we listen, sir?
Okay. You are having a college schedule in the morning hours?
Yes, sir.
Okay.
Sir.
Yes, please.
So for how many days will the morning session will be continued, sir? Because we have college from 8 to 5 o'clock, sir.
Okay. Now, regarding the morning session, I can't comment anything. Okay. The office person will let you know.
We completely missed
Okay.
the power system, sir.
Yes, actually, we are missing completely morning sessions. Evening session, we can manage at least 1.5 hours or 2 hours, but morning session, we are completely
We are
missing.
completely missing morning hours, sir.
Okay. Okay.
Sir,
ठीक है, then most of the students are saying that sir it should be from 5 to 9 only, right?
Sir,
I will communicate your message to the office, right?
sir,
Yes, please.
sir, rather than making it from 5:30 to 9, like you can make it from 5:15 and reduce the break amount by like 10 minutes. Still, it can be compensated, no, sir.
We can start at 5:15.
So it's somewhere between those for those who can't attend and those who can attend, and then make it till 9 by reducing the break time by 10 minutes.
Okay. 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 So don't cut break again. If you are saying sir, don't cut break. Okay. Anyways, I will communicate your message, right? So from 5 to 9 only we are going to continue. Right. Good evening. Yeah, announce kiya, but the students are saying that 5 to 9 is okay. They are not ready for 5:30. Very few students are ready for 5:30 to 9:30. Same time, na? Same time. Yes. Okay. Yeah. Okay. Yes. Okay. Yes. ठीक है, right? Because it is very difficult to fulfill the requirement of all the students, right? So we're trying at our level best. Anyways, most of the students are saying that from 5 to 9 only. So we'll continue for 5 to 9 only, right? Okay. So next, let us discuss the buck converter. Okay. In the yesterday session or day before yesterday, we discussed about the two basic choppers, step down and a step up chopper. Okay. Again, the step down chopper, step up chopper, or your step up, step down chopper. Okay. If we add a inductor and a capacitor in the circuit, then it will be referred as a buck converter, boost converter, and buck boost converter. Okay. So let us put the heading buck converter, buck converter. Yes. So the circuit diagram for the buck converter. Yes, the chopper is having a limitation or the drawback like the voltage across and the current flowing through the load. Okay, it will be changing suddenly, na? Right? For some intervals, we discussed in the step down chopper. Okay, or you can check in a step up chopper also. In some intervals, we'll be having the zero voltage, right, and a zero current also, right? So that as it is the output of that chopper circuit, we cannot give as an input to the load, right? So for that, we are going to add the inductor and a capacitor in the circuit, right? So okay, so here we're having a DC voltage Vs. Next, same circuit as that of your step down chopper. Here it is a diode and an inductor here. The load, it may be anything, because at the end we are going to get a constant voltage and a constant current now, because it is a DC to DC converter, right? So for analysis purpose, we are going to consider the load is a resistive only. Voltage across load V0, current flowing through the load is I0, current flowing through the capacitor is IC, voltage across capacitor is a VC, voltage across inductor is a VL, current flowing through inductor is a IL, current flowing through diode is a ID, and here we are having a switch. Consider this voltage is VSW and ISW, switch current, and the source current is a IS. Okay, so if you check the step down chopper and this buck converter circuit, okay, you will understand that yes, here we have connected a capacitor across the load. Why we have connected the capacitor across the load? Because we know the capacitor is the element which opposes the change in the voltage, na? Right? So if we are interested in opposing the sudden change in the voltage, because in the step down chopper we discussed that, yes, if you recall in the step down chopper, we had a waveform like this. Just a minute. Yes, it was like suddenly decreasing na, at T on, and again it will be 0 for T on to T, right? Means when switch was in off state, it is like a voltage across the load was a 0. And at the same time here, you can check the current, okay? Current flowing through the load is also having a 0 interval, right? So in order to avoid that, we have connected an inductor, right? And a capacitor. Capacitor is connected across the load because we are interested in improving the V0 waveform, and inductor is connected here. Okay, you can say that inductor is connected in series with the load actually. Okay, now while doing this analysis, we are going to consider the load current and load voltage is a constant. Okay, so these are our assumptions. Okay, assume V0 is a constant and I0 is also constant. Now you might be thinking that, sir, for purely resistive load, how can be the I0, right? Will be a constant, right? So here you can check. This is a DC to DC converter. Input is your fixed DC, and by controlling the pulse width, by controlling the duty cycle of this switch, okay, we are going to vary the output. Okay, so output is also DC because input is DC, output is DC. It is a DC to DC converter. Okay, so as we are interested in getting the constant output voltage, right? So that's why we are having the assumption like V0 is constant, and if V0 is constant, definitely your I0 is also constant. Okay, so V0 is constant, I0 is constant. Okay, now as long as this circuit is considered, we are going to follow the 14 steps. Okay, so which are those 14 steps? Let me first write. And for buck converter, boost converter, buck boost converter, we are going to follow these 14 steps only. Okay, and those 14 steps consists of the detailed analysis of your respective converter. Okay, and if you check the previous GATE, previous ESC examination or PSU examination also, okay, all of the questions, okay, can be solved, right, based on those 13 steps only, 13 to 14 steps only, right? So let me highlight those steps first. When switch is on, yes, we are going to find VL and IC. VL means voltage across inductor, and IC means current flowing through the capacitor. Okay, VL and IC. Yeah, let's go. VL and IC. Okay. Second, when switch is off, find VL and IC. Okay. So first of all, we need to consider the switch is in on state, and again applying the KVL, we are going to find the VL expression. By applying the KCL at a particular node, we are going to write the expression of the IC. Similarly, when switch is in an off state, right, we are going to, by applying the KVL, we are going to find the VL voltage, that is voltage across inductor, and IC, that is the current flowing through the capacitor, by using the KCL. Okay, so these are the first two steps. Third step, we are going to write the volt second balance equation. Volt second balance equation. What is the volt second balance equation? We discussed in the yesterday's session or day before yesterday's session. We know the average voltage across inductor is 0 na, right? So we wrote there, it is like 1 by T integration from 0 to T, VL into dt is equal to 0, right? And that 0 to T we divided as 0 to T on plus T on to T na, right? So it is like voltage across inductor into the time. So that's what is the volt second balance equation. Similarly, we are going to write the current second balance, ampere second balance equation, okay, for the capacitor. Okay, volt second balance equation, this is for inductor and ampere second balance equation. Ampere second balance equation. This is for capacitor. This is for capacitor. We'll discuss why how to write the ampere second balance equation. Okay. Next, the fifth step is ripple in inductor current, delta IL. Ripple in inductor current, delta IL. Sixth step is finding the value of IL max, okay, and IL min. So this is a IL max, that is the maximum value of inductor current. Maximum inductor current. And seventh is IL min, that is the minimum inductor current. Minimum inductor current, right? How to find delta IL and how to write IL max, IL min, we are going to discuss, okay? Minimum inductor current. Next, source current, IS. Definitely the IS is nothing but it is a IS average only because input side is we are having a DC, okay, and effective value is a average value, okay? Source current. Next, switch current. Yes. Switch current, okay, this is the ninth one. 10th is a diode current. ID. 11th is the ripple in capacitor voltage, that is a delta VC, or you can write it as a delta V0 also. This is nothing but ripple in capacitor voltage. Ripple in capacitor voltage, okay. 12 is the D at which duty cycle. Duty cycle D at which ripple is maximum. Ripple is maximum. Okay. 13, L critical and C critical, right? Critical value of inductance. That is a critical inductance. And 14 is a critical capacitance. Okay. So these 14 steps, right, we are going to follow in order to analyze the given regulator. Okay. So regulator, or you can say the converter. Okay. So that might be your buck boost or buck boost. For all the three converters, we are going to follow these 14 steps, right? We are going to follow these 14. It is very easy, right? Please be focused. Don't lose your concentration. Okay. So here, because compared to the rectifier, in the rectifier, we had a AC supply, na? Right? But here you can check we're having a DC supply, right? So as long as the supply is considered, your analysis is comparatively easy here. Okay. Nice. But the thing is, you need to be, if your basics are perfect, you need to be perfect with the basics as long as your networks are considered. Okay. So we'll discuss here. So as I said, Vs is the supply voltage. It is a constant voltage. Okay. V0 and I0 were assumed. These are the constant. These are the constant only, right? So now let us understand first, before proceeding, what is the Holt second balance equation and what is the ampere second balance equation. Okay. So let me write it as first Holt second balance equation and ampere second balance equation, right? So Holt second balance equation. Yes. As we know, the average voltage across inductor is always 0. Yes or no? Average voltage across inductor is always 0 volt na, right? Because we know for some interval inductor stores energy. At that time the polarity of the voltage across inductor is like, suppose left side plus, right side minus. Okay, then when inductor releases the energy, what happens? The polarity will be reversed. Okay, and we know the average energy as well as average voltage across the inductor is 0. Okay, so for that, how we write average voltage, right? So it is a 1 by t integration from 0 to t VL into dt is equal to 0. Same thing we wrote in the Saturday session. Okay, so this can be written as 1 by t into 0 to t is having 0 to t on, yes or no? This is a VL during on state into dt plus integration from t on to t VL during off state into dt is equal to 0. Please try to understand. What is this VL on? VL on is nothing but the voltage across inductor during the on state of the switch. VL off is the voltage across inductor during the off state of the switch. Okay, so further we can write, therefore if I shift this t to the right hand side, it will be like 0 into t na? So that 0 into t will become 0 only, right? So can I write it as VL on into, it is like a t on minus 0 plus VL off into, it is like a t minus t on is equal to 0. Yes or no? So what it indicates? It is like a VL on into t on plus VL off into t minus t on means what? Total time minus on time. That is nothing but the off time of the switch na, into t off is equal to 0. So what this equation indicates? This is nothing but your Volt second balance equation. You can check voltage across inductor during on time into on time, that is the Volt second na, plus voltage across inductor during the off time into off time, that is again Volt second, that is equal to 0. This is nothing but your Volt second balance equation. Volt second balance equation, right? Volt second balance equation.
అమ్మా వాళ్ళ పెన్నుల డబ్బా తెచ్చుకోవాలి కదా, తెచ్చాము.
Please mute your audio, right? Okay, okay. So Volt second balance equation, VL on into T on plus VL off into T off is equal to 0, right? Next, similarly, we are having the ampere second balance equation. So let me write the ampere second balance equation. So as I said, Volt second balance equation is associated with your inductor, na? Right? And ampere second balance equation, it is associated with the capacitor. In the case of inductor, average voltage is 0, but in the case of capacitor, average current is 0. Please keep it in mind. Okay, because if you recall, suppose I am having a capacitor here, let us consider C. So and suppose across this capacitor, let me consider this type of circuit. As long as this, suppose at t is equal to 0, this switch is closed. Okay, at t is equal to 0, this switch is closed. Then what will happen? After that, our capacitor starts charging na? Okay, so when capacitor charges, what is the direction of current flowing through the capacitor? It is like this, that is in a downward direction. Yes or no, right? So this is the direction of the capacitor current when capacitor charges. But suppose capacitor charged to the full voltage, okay, that is equal to Vs volt. Now consider the capacitor charged to the voltage of Vs volt. Now in order to discharge it, suppose I am reducing this voltage. I am reducing this voltage, means suppose from Vs volt, I have reduced this voltage to, let us consider it as a 1 by 2 Vs volt. So when capacitor discharges, how is the direction of the capacitor current? Whether it will be in the same direction or whether it will be opposite? Definitely, yes, it will be in the opposite direction. Na? So in the case of capacitor, always keep it in mind. Yes, during charging and during discharging, the capacitor current is opposite. Whereas if you recall in the inductor is the element which opposes the change in the current. Okay, so when inductor stores energy and as well as when inductor releases energy, in both the cases, the inductor current direction is the same only. I am saying inductor current direction is same. In the case of capacitor, when capacitor charges and when capacitor discharges, the polarity of the voltage across capacitor is the same only. You can check when capacitor charges, it is like plus here, minus here. When capacitor discharges, it is like same plus minus. The thing is current flowing through the capacitor is reversible. Okay, so in the case of capacitor at steady state, in the case of capacitor, yes, the average voltage across capacitor is 0. Okay, average voltage across capacitor is 0. Sorry, average current flowing through the capacitor is 0. So let me write here, average current through the capacitor is a 0, right? So we can write it as yes. So average current through capacitor is 0, right? So average current through capacitor is equal to 0, right? So we can write it as 1 by t integration from 0 to t. It is a IC into dt is equal to 0. What is this indicates? 1 by t integration of 0 to t IC dt. It is the average current, average value of the IC, na? Right? So this can be written as, therefore 1 by t integration from 0 to t on. It is a IC into dt plus integration from t on to t. Okay, it is again IC into dt is equal to 0. Let me indicate it as IC on. Let me indicate it as IC off. Okay, IC on dt, IC off dt. Okay, what will the value of your IC on? What will the value of IC off? It depends on your circuit. Okay, right? We are going to discuss it, how to find your IC on and IC off. So therefore, this t, if you shift it to the right hand side, so 0 into 2, that will be 0. Okay, so I can write it as IC on into t plus IC off into t is equal to 0. This is nothing but your ampere second balance equation. Ampere second balance equation. You can check in this equation, we're having a current into time. So it is an ampere second plus current into time. It is again ampere second. Okay. So product of ampere second during the on time of the switch plus product of ampere second during the off time of the switch is equal to 0. Is equal to 0. Okay. So now, yes, this is ICT on into T plus ICT off into T is equal to 0. Okay. Next, now yes, here it should be T on. Sorry, here it should be T on and T off. Correct. T on and T off, and here also, yeah, I have written just T on T off. Correct. It should be T on and T off because upper limit is T on, and here it is T minus T on means T off only. Okay, correct. Yes. So this is the ampere second balance equation. So please try to understand, ampere second balance equation is whole second balance equation is related to your inductor. Okay, related to the inductor, right? So now let us discuss the circuit operation. Yes. So we're having this circuit. This is the buck converter. Okay, this is the buck converter. Now, so very first step we wrote here is, when switch is on, find VL and IC. Okay, so when switch is off, when switch is on, okay, we need to turn on the switch and we need to find the VL and the IC value. Okay, so for that, let me draw the same circuit again, right? So just a minute. Yes. So when switch is in an on state, right? Okay. So first here we need to put the switch is in a on state. Switch is in a on state, right? Very first step we're having switch is in a on state, right? So I have turned on the switch here. I have turned on the switch here. So here you can check first step when switch is on. When switch is in a on state. When switch is in a on state. So now when switch is in a on state, what will happen to this diode? This diode, yes, will feel the reverse voltage na, and diode will be in a off state only, right? So here the diode D will be like a open circuit. Diode D will be like a open circuit. Okay, so diode D is a open circuit. What will happen in the circuit? You can check when switch is in a on state. It is like current is flowing into this loop. It is like our inductor go on storing the energy. Inductor go on storing the energy. Okay. At the same time, what will happen to the capacitor? Okay. What will happen to the capacitor? That will be determined the value of the IC. That will be determined by the value of IC. Okay. We'll discuss. So here you can check when switch is in a on state, diode is in a off state, diode D is in a off state, diode D is in a off state, right? So now for this circuit, can we write VSW is equal to 0 volt? VSW is equal to 0 volt. Next, can we apply KVL to this loop, KVL to the outer loop? Yes, we can apply KVL to outer loop. Let me write KVL to outer loop, KVL to outer loop. It is like a plus VS minus VSW minus VL minus V0 is equal to 0 na. Out of that, VSW is 0 only. So therefore, what is VL? VL is equal to VS minus V0. That is the source voltage minus load voltage is nothing but your voltage across the inductor. Okay. So for the first step, yes, we have written the value of VL here. Okay. By applying simple KVL, simply KVL. Next, now here during this step, during the first step, yes, what is the IC here? Can we write? Apply KCL at this node. Let me consider it as a node X. KCL at node X is IL is equal to IC plus I0 na? Yes or no, right? So can I write IL is equal to IC plus I0. KCL at node X. KCL at node X. So it will be like IL is equal to IC plus I0. Therefore, we can write it as a IC is equal to IL minus I0. IL minus I0. This is your capacitor current. This is the capacitor current when switch is in a on state. When switch is in a on state. Okay. So please try to understand when switch is in a on state, what is happening into the circuit? Your inductor is storing the energy. Inductor is storing the energy. Okay. So let me write here inductor L stores energy. Inductor L stores energy. Inductor L is storing the energy, right? So when inductor stores energy, what about the IL waveform? Whether it will be increasing or decreasing? Yes, can anyone? My question is when inductor stores energy, the IL waveform will be increasing or decreasing? That is di by dt. Specifically, it will be positive or negative. It will be increasing, na? Right? We have discussed, right? When inductor stores energy, IL is yes, IL is increasing. That is nothing but your DIL by dt is a positive only. DIL by dt is a positive only. Okay, you can check here. We're having VL is equal to VS minus V0. Okay, so actually this is your buck converter. So at the end, we will be getting the expression of V0 average. In that case, you will understand it is same method of your step down chopper also. In the step down chopper, we're having the expression V0 average is equal to D into VS na. Same expression will be getting here. Same expression will be getting here. Okay. So inductor stores energy. Next, what about the ID here? What about the ID? When switch is in a on state, ID is 0. Can I write? Yes. ID is equal to 0. Diode current is equal to 0 ampere. Next, what about the ISW? Can I write IS, ISW and IL all will be same? Yes or no? Right? IS, ISW and IL all are same because same current is flowing into this branch, na? Right? So IS is equal to ISW is equal to IL. All the currents are same, right? All these currents, these three currents are same. Okay. Now, yes, VL we have written, IC we have written. Okay. Second step, when switch is in a off state. When switch is in a off state. Okay. So let me write here. Second step, when switch is off. When switch is in a off state. So you can check this circuit. When switch is in off state, what will happen means it is like this will act as an open circuit. This will act as an open circuit. Okay. So whether our inductor will allow the change in the current, because when switch was in on state, now that is like from t is equal to 0 to t on. Switch is on means t is equal to 0 to t on. Okay. So inductor current was like increasing. Inductor current was like increasing. When switch is in an off state, whether our inductor will allow the current to change, okay, from that peak value to the zero value? No. So what will happen? Our inductor will go on releasing the energy through this diode na. So when switch is in off state, diode D will be in a on state only. Yes or no? Right? Please try to understand. Okay. So when switch is in a off state, inductor releases energy. Diode D is in a on state. Diode D is in a on state. So let me write here. When switch is in a off state, that is nothing but time is your t is equal to t on to t. T on to capital T. Right? Next. So here switch is in a off state. Switch is in a off state. So equivalent circuit will be like this. Switch is open. Here it is a supply voltage Vs. Diode is in a conduction mode. Inductor releases energy. What will happen to the capacitor? We'll discuss. So this type of circuit we'll be getting. This is the diode. Vs. ISW. This is your VSW. This is ID, inductor L, VL, capacitor C. Be careful. I am not reversing the polarity. Okay. I am not reversing the polarity of the VL. I am keeping the VL as it is. Also in the rectifier chapter also, we kept the VL polarity as it is. Okay. In as long as power electron is considered throughout the circuit analysis, we are keeping the polarity of the voltage across inductor same. We are not reversing it. Okay. So please. So this is a VL. Okay. This is a IC. Voltage across capacitor is VC. R. V0. This is a I0. Okay, so we'll be getting this type of circuit. Actually, the thing is what is happening here, inductor is releasing the energy. This is your IL, na? IL. Inductor releases energy. So let me write here, inductor releases energy. Inductor releases energy. Okay, so inductor releases energy means definitely current flowing through the inductor should decrease. Okay, current flowing through the inductor should decrease. Are you getting the point? Okay. Now here diode is in a conduction mode. So diode is in a on state or a conduction mode. Diode is in a conduction mode. Next, now can we apply KVL to this loop? I'm saying only to this loop. KVL to this loop. Yes, it is like a minus VL minus V0 minus voltage across the on state diode. It will be 0 only. Okay, so it is minus VL minus V0 is equal to 0. Okay, so KVL to loop. So I'm writing it as minus VL minus V0 is equal to 0. So you can write here, therefore, VL is equal to what? It is a minus V0. Right? Minus VL minus V0 is equal to 0. So VL is equal to minus V0. We are getting VL is equal to minus V0. Is this clear? Right? Next, again, for getting the IC expression, let us consider this node is X. Can we apply KCL at node X? Yes, KCL to node X. KCL to node X. So we can write IL is equal to again IC plus I0. I am not reversing the direction, okay, of the IC. I am keeping the direction of the IC same. I am keeping the polarity of the voltage across inductor also same. Okay, same. So IL is equal to IC plus I0. So therefore IC is equal to, it is a IL minus I0. IC is equal to IL minus I0. Right? This is the one thing. So we have written IC expression, we have written VL expression. Now, yes, now here, can I say that IL is equal to ID because current is flowing into this loop and whatever the current here, the same current is flowing here. So can I write ID and IL both are same? Yes or no? Right? So ID is equal to IL. ID is equal to IL. Next, from this circuit, can I say that IS and ISW both are 0? Yes or no? IS and ISW both are 0. Okay, because switch is open, right? So IS is equal to ISW is equal to what? 0 ampere. Okay, it is a 0 ampere. Now what is the VSW here? You can apply KVL to this loop. You will be getting plus Vs minus VSW is equal to 0. So VSW is only Vs na, right? So VSW is equal to Vs. VSW is equal to Vs. Now, yes. So these are the equivalent circuits or the first two steps. When switch is in an on state, what we have done? Simply we have closed the switch. You can check here. I am revising it. When switch is in an on state, simply close it. Diode will fill the reverse voltage. Diode will be in an off state. Current will be flowing like this. It is like inductor is storing the energy. Okay. For that we have written IL, ISW, IS. All are same only. Right. Next, so from this we have written the expression of VL by applying KVL. Na? So we wrote VL is equal to Vs minus V0. Simply apply KCL here. You will be getting IL is equal to IC plus I0. IL is equal to IC plus I0. Right. Next, other things like ID is 0 ampere. Okay. Right. Those are the additional things we wrote here, because in order to draw the waveform of those things like a VSW, IS waveform, ISW waveform, ID waveform, right? We require those values. So that's why those additional things I have written here. Okay. This is the first step. Second step, when switch is in an off state, that is switch is like an open circuit. So current will be flowing only into this loop. Inductor releases energy. Inductor releases energy. Okay. So here you can check inductor is releasing the energy. IL is equal to ID. VL we got VL is equal to minus V0. Now you can check here. I am keeping the polarity of the VL same. But in this case, I am getting VL is negative. I am getting VL negative with this polarity. The meaning is what? Your VL actual polarity is like plus here and minus here, na? Yes or no? Right? So the thing is, as long as our power electronic circuit analysis is considered, what I am doing, I am not changing the polarity of the voltage across inductor. I am keeping the same polarity. But what we are getting when inductor stores energy, we are getting that VL is positive. And when inductor releases energy, we are getting that VL is negative. Are you getting the point? This type of things we are getting. Okay. Next. So here we are having VL is equal to minus V0. Now, yes, in addition, we have written IC is equal to IL minus I0 by applying KCL to the node X. ID is equal to IL. Definitely VSW is equal to VS. IS and ISW both are 0. Next, third step, Holt second balance equation. Okay. Holt second balance equation. Let me write. Holt second balance equation. Holt second balance equation will give you the expression of V0 average of the buck converter. Okay, V0 average of a buck converter. Okay, so Holt second balance equation. What is the Holt second balance equation? We know it is a VL during on state into T on. That is voltage across inductor during on state. That is when switch is in on state. Okay, into on time of the switch plus voltage across inductor during the off state into T off is equal to 0. Yes or no? This is the Holt second balance equation, right? So you can check Holt second balance equation we wrote here. The same equation here, VL on into T on plus VL off into T off, okay, is equal to 0. Now, VL on means what? Voltage across inductor when switch is in a on state, na? So when switch is in a on state, what is the voltage across inductor? We wrote here. When switch is in a on state, voltage across inductor is Vs minus V0, na? Vs minus V0. So can I put here Vs minus V0 into T on, okay, into T on plus voltage across inductor when switch is in off state. So when switch is in off state, that is this state, okay, voltage across inductor is minus V0, na? So let me write it as a minus V0 into T off is equal to 0, right? Now, can we replace this T on? Can we replace this T on in terms of duty cycle D and a total time T? Because we know, yes, you can check, we are having here D is equal to T on by T, na? So therefore, can I write T on is equal to D into T? Yes or no? Right? T on is equal to D into T. So I am writing it as, therefore, Vs minus V0 into dt, right? T on is nothing but dt minus this V0 as it is into T off. T off means what? we know total time t is equal to t on plus t off na. So therefore can I write t off is equal to t minus t on? Yes, so I can write it as t minus t on is equal to 0. Is this clear? Means I have replaced this t off with a t minus t on only. Next, so further what we can write? Yes, simply take the multiplication vs into dt, okay, minus v0 into dt minus v0 into t, right, plus v0 into t on. T on means again, can I put it, or let me write as first t on, in the next step I will put it as a dt. Please check vs dt minus v0 dt minus v0 t plus v0 t on. Further we can replace this t on with the dt. So it is the vs into dt minus v0 into dt minus v0 into t plus v0 into dt na, is equal to 0, right? So can I shift this vs this v0 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 all v0s to the right hand side? Yes. So therefore, or before that, this is plus v0 dt, this is minus v0 dt, it will get cancelled out. Okay, so therefore we can write vs into dt is equal to what? V0 into t. So what it indicates from this, we can write, yes, v0 is equal to d into vs. Yes or no? So you can check this expression. This v0, we assumed that v0 is constant na? Yes or no? This v0 expression is a v0 average only, because you can check wherever vs supply voltage is a dc na, it is a constant dc. Okay, so can I say that this v0, you assume the v0 is also constant, so this v0 means what? It is a v0 average, which is equal to duty cycle d into vs. Step down chopper expression, in that case also we wrote v0 average is equal to d into vs. Okay, means even though we have connected an inductor and capacitor in the circuit, but then also whether our output voltage has changed? No, we are getting the same output voltage, but the thing is we are getting the improved v0 and improved i0. Okay, means we are getting the constant v0 and constant i0. How we are getting constant v0, constant i0, yet I have not discussed it. Okay, right, at the end we will discuss. Is this clear? So this is the v0 which is equal to d into vs. V0 is equal to d into vs, right? So always keep it in mind. Volt second balance equation gives you the average value of the output voltage. Okay, expression for the average value of output voltage. Next step, we're having the ampere second balance equation. Ampere second balance equation. So let me write, yes, ampere second balance equation. I think step number 4, right? Ampere second balance equation. Yes. What is the ampere second balance equation? Current flowing through the capacitor during on time into T on plus current flowing through the capacitor during the off time into T off is equal to 0. This is your ampere second balance equation, right? What is the current flowing through the capacitor during on time? We have written it is a, yes, during on time we are having IC is equal to IL minus I0 na. Again during the off time also you can check, we are having during off time. What is the IC? Off time is this one. Okay, switch is off. So during this also you can check IC is equal to IL minus I0. Means in both the cases we are having IC is IL minus I0 only. Okay, so can I write it as IL minus I0 into T on means dt, right? Which is equal to IL minus I0 into T off. T off means T minus T on is equal to 0 na, right? So further we can write it as IL minus I0 into dt plus IL minus I0 into T minus dt na, is equal to 0. So therefore can I write it as, yes, it is like a IL minus I0 into dt plus IL minus I0 into T. Okay, I'm multiplying with T first. Next minus IL minus I0 into dt is equal to 0. I have multiplied this bracket with the T first, then minus dt. Okay, minus dt. So you can check this term and this term, it will get cancelled out. Yes or no? Plus minus. So therefore I can write IL minus I0 into T is equal to 0. So therefore, can I say that IL is equal to I0? 0 by T means 0 only, na? So therefore, IL minus I0 is 0, means what? IL is equal to I0. So what it indicates? We assume that the load current is constant. So this I0 means what? Your I0 average. We are getting the I0 average. Okay. So this is the I0 average. So please try to understand what it indicates. Average value of load current is equal to your IL. But we are having IL, whether IL is constant, no, IL we are having changing, right? Increasing, decreasing, increasing, decreasing. We discussed when switch is in an on state, inductor stores energy. When switch is in an off state, inductor releases energy, na? So can I say that this IL means what? That is nothing but your IL average here. This IL means what? IL average here. Okay. So let me write here. This IL means IL average. So let me write it as I0 average is equal to IL average. Right? So this is the ampere second balance equation. So please keep it in mind. They have asked a very straightforward questions. Further, they will give the circuit like a buck converter. Okay, they will give the values, load current and those things, or duty cycle supply voltage. Okay, load register they will give, and they generally ask what is the average value of inductor current. Then simply here, inductor current average value is equal to what? Your load current average value. IL average is equal to I0 average. Okay, so this is the ampere second balance equation. Okay, ampere second balance equation. Next, now can we draw the waveform of IL, I0 and IC? Yes, we can draw. Yes, please listen. IL waveform, how it is. IL, time t, 0, 0 to t on to t, and t to t plus t on. Okay. And next, let me draw the waveform of IC also. Let us draw the waveform of first I0, let us draw, and after that the IC. Yes. Yes. So how will the waveform of IL? How will be the waveform of IL? You can check during 0 to t on. Inductor current, inductor is storing the energy. So IL is increasing, na? IL is increasing. Okay. So here IL will increase from minimum value to the maximum value. Please try to understand this. This is your I1 and this is your I2. Inductor is changing from I1 to I2. Definitely for very first cycle, it will start from 0. But this is a continuous cycle. This is a continuous cycle. The meaning is inductor is storing the energy. Inductor is storing the energy, and inductor current is changing from I1 minimum value to the maximum value. During T on to T, what happens? Inductor releases energy. Okay. So again, inductor current will change from, or will decrease from I2 to I1. And again, for the next on time, it will again increase from I1 to I2. So this is, yes, we are having, this is I1. This is a steady state operation I am writing. Right? For the next off time, again it will decrease. Again it will decrease. Means the inductor current is changing from I1 to I2 and I2 to I1. I1 to I2, I2 to I1. Right? Means inductor current is varying between I1 and I2 only. Between I1 and I2 only. The thing is, what we are doing here? Yes, we are going to select the T on in such a way that, yes, if the switch is turned on, the inductor current will increase from I1, and when it reaches to the I2 value, at the same instant, we are going to turn off the switch. When switch is turned off, inductor current go on decreasing. When it reaches the minimum value, that is the I1 value, again we are going to turn on the switch. Okay. So during turn on increases, during turn off it is decreases. Okay. So I1 to I2, I2 to I1, I1 to I2, and again same. So this is your IL. Now, what will be the IL average waveform here? IL average waveform. Suppose for this waveform, I want to draw the IL average waveform. How it will be? Average value of the inductor current. Well, first thing is whether this IL, okay, whether this IL, right? You can check this IL is a linear or non-linear. Because across the inductor we're having a DC supply, na, right? And we discussed in the yesterday session also. Yes, as your di by dt is a constant, na, right? It is a Vs by L something. Okay, so that's why what is happening, or Vs minus V0 by L. Vs is a constant voltage, V0 is also constant voltage. Okay, so Vs minus V0 by L. So that difference is constant, divided by L is also constant. Okay, so di by dt is constant, means it is a linearly changing. Linearly changing. Are you getting the point? Okay, so average value of the inductor current, yes, it will be exactly passing through the center of this. Okay, exactly passing through the center of this. Okay, so let me write it as IL average waveform. Draw this. This is your IL average waveform. IL average. Suppose we are having a waveform like where the current is changing from 1 ampere to the 3 ampere linearly. Yeah? Suppose I am saying that we are having a current which is changing from 1 ampere to the 3 ampere, and again it is changing from 3 ampere to the 1 ampere, again increasing from 1 to 3, again decreasing from 3 to 1. So what will the average value? It is a 2 ampere, na? Yes or no? Right? So similarly here we are, yes, drawing the IL average which is passing through exactly the center point, exactly through the center point. And how to find that IL average expression, right? We are going to discuss. IL average is I1 plus I2 by 2 and those things. Okay, so next, now I0, we have written I0 average and IL average both are same, na? So if IL average is this one, definitely I0 average or I0 waveform is also like this only. Keep it in mind, we have assumed that average value of load current is constant, na, right? Sorry, we have assumed that the load current is constant, load voltage is also constant. Okay, so that's why load current waveform will be like this only, and it is same as that of your IL average. So please try to understand this. This is your I0 average, which is equal to IL average. Okay, I0 average which is equal to IL. Let me indicate it with a capital I0, right? Let me indicate it with a capital I0, right? Next, so this is your I0. Now, how will the waveform of IC? How will be the waveform of IC? Because you can check when switch is in an on state. What is IC? When switch is in an on state, IC is IL minus I0. Now we have written. You can check here. When switch is in on state, it is IL minus I0. When switch is in off state, also it is again IL minus I0. Na? Yes or no? Right? So you can check IC waveform, which is equal to IL minus I0. IL waveform, yes, you can check. IL waveform is like this. I0 waveform is this one. This waveform, this magnitude and this magnitude, red one, both are same or different? Both are same only, na? Both are same only. Okay. So now if I want to draw the IC waveform, how it will be? At t is equal to 0. At t is equal to 0, you can check. At t is equal to 0. IL, this is like your IL waveform. Okay, this is the IL waveform, and this is your IL average waveform, na? IL average is again is equal to I0 average. Okay, that is the constant current. Now at t is equal to 0, what is the IL minus I0? At t is equal to 0, what is the IL minus I0? At t is equal to 0, IL is I1, na? Yes or no? Right? So IL is I1. So IL minus I0 will be like this value minus this value, na? Because IL average and I0 average both are same. Yes or no? So can I write at t is equal to 0? Yes, IC is equal to IL minus I0 means I1 minus this value. So whether it will be positive or negative, that will be negative, na? That will be negative. Okay. So what is the magnitude of that term? Negative term. We'll discuss. Okay. So please here consider this is I2, this is I1. Okay. Let me consider this difference. I2 minus I1 is equal to your delta IL. I'm writing it as a delta IL. Okay. What is delta IL? Delta IL is equal to I2 minus I1. It is known as peak to peak ripple current of the inductor. Okay. Peak to peak ripple current of inductor. You can check in the procedure also we have given delta IL, right? That is the ripple in inductor current. What is the ripple in inductor current meaning is, yes, minimum inductor current and maximum inductor current, the difference between the two is nothing but your delta IL. Delta IL. Okay. So delta IL means what? I2 minus I1. That is the maximum value of the inductor current minus minimum value of the inductor current. That is nothing but the delta IL. Now my question is, yes, at t is equal to 0, at t is equal to 0, this value is I1, IL value is I1. Okay. And I0 average is like your IL average. That is this value only. Yes or no? So what is the difference between IL and IC? It is I1 minus this value. So can I say that the difference between these two is nothing but your delta IL by 2? Because it is exactly passing through the center now. So can I say that, yes, before this line or I1 minus I1 minus this IL average or the I0 is nothing but your delta IL by 2, right? So this difference we can represent it as a minus delta IL by 2. This is a minus delta IL by 2. Just try to understand this point. This is minus delta IL by 2. Let me write it as a capital. Okay, minus delta IL by 2. Right, because it is I1 minus this value. So this difference is like your delta IL by 2. This full difference is delta IL. So exactly it is a delta IL by 2. Okay, so it is minus delta IL by 2. Next, after 0, as we are increasing the time corresponding to this instant, you can check corresponding to this instant, right? Yes, at this instant, what is happening? IL and I0 both are same or different? IL and I0 both are same. So what is the difference? IC is equal to IL minus I0. So difference between the two same values. So it is equal to 0. So that's why as we are increasing, we'll be getting this type of IC. As we are increasing, we'll be getting this type of IC. At this instant, it will be 0. At this instant, it will be 0. So it will be like this, passing through the 0. As we increase, as we reach towards the T1, at T is equal to T1, you can check IL is I2 and I0 is constant value. Na? So I2 minus this value means the difference is plus delta IL by 2. So it will be from here, it will increase to plus delta IL by 2. So this is like your plus delta IL by 2 plus delta IL by 2. After that, what will happen? Again, inductor current is decreasing. So inductor current is decreasing means what? The difference between IL and I0 is a decreasing now, because IC is IL minus I0. Okay, so we'll be getting the IC waveform that will be like this. Corresponding to this instant, yes, it will be 0 and we'll be getting this type of waveform. Right? Again, it will be reaching minus delta IL by 2. Corresponding to this instant, again it will be passing through 0. And again this instant. This is a plus delta IL by 2. And this is a minus delta IL by 2. Yes or no? Please try to understand how we have written, how we have drawn this waveform. We are having IC is equal to IL minus I0, but our I0 is constant now. So it is IL minus capital I0, IC. And you can check IL average and I0 average, both are same. Okay. So that's why instead of taking difference between these two, this one and this blue line, I'm taking the difference between this red and this blue. Okay, because this red and this red both are same, right? So here we are having the waveform for IC, waveform for IC. Now, as it is exactly passing through the center point now, here and here, this total is your T on. From here to here, it is a T on. Okay, so can I indicate? Yes, from this point to this point, it is a T on by 2. And from here to here, it is a T off by 2. T on by 2 and T off by 2. Means from this point to this point, we can check it is a T by 2. This will be your T by 2. Okay, this will be the T by 2. Okay. Now, so here we are having a IC waveform, I0 waveform, IL waveform. Now, can we draw the VC waveform, voltage across capacitor waveform? How it will be? VC waveform. Time T, 0 to T on to T, T to T plus T on, and so on, right? And so on. Now you can check capacitor charges and capacitor discharges. Capacitor charges and capacitor discharges. Okay, it will be determined by the direction of the current flowing through it, na? Yes or no? Right? So if you check this circuit, if we check this circuit, yes. If can I say that if IC is positive, it is like capacitor is charging. If IC is negative, it is like capacitor is discharging. Yes or no? Please try to understand. If IC is positive means we have written, right? We have drawn the IC waveform, and from that waveform we are going to draw the VC waveform now. Okay, so please try to understand. In the IC waveform, we are having IC negative as well as positive, na? Right? So we are discussing when IC is positive. When IC is positive, can I say that IC positive means IC is in a downward direction? Can I say that capacitor will be charging? And when IC is negative, that is current IC is upward direction. Okay, means IC negative. Then can I say that capacitor is discharging? Yes. Okay, so please try to understand. Let me write here. IC positive means capacitor charges. Capacitor charges. And IC negative means it is like a capacitor discharges. Capacitor discharges. Now from this, yes, we are going to draw the waveform of VC. So you can check here from omega t is equal to 0 till this instant. Okay, this instant is like t on by 2. From this point to this point, we are having a t on na. So it is like exact center point. So it is a t on by 2. So 0 to t on by 2, it is like IC is negative, means the capacitor is discharging. And from this point to this point, IC is positive na. So it is like capacitor is charging. Capacitor is charging. So let me write here. It is like from 0 to t on by 2. T on by 2 means somewhat here. Okay. And from this point till you can check this instant. This instant is like a t. Okay. This instant is like a t. So it is t on to t, right? T on to t. Okay. So yes. So it is a capacitor discharges. So capacitor will discharge slowly. So capacitor voltage is decreasing means capacitor is discharging. After that, from this point to this point, it is like you can check IC is positive, na? This is from t on by 2 till this t, na? Till this instant. It is like a t off by 2. Okay, t off by 2 means till this instant, somewhat here. Okay, it is like capacitor is charging. So capacitor charging means the voltage will be increasing like this. Okay. Again, after that, it will discharge, na? Again, after that, it will discharge and again charges, right? And so on. Is this clear? Means how we have drawn the VC waveform? Yes, from IC waveform, we have drawn the VC waveform. IC negative, so that's why I have taken capacitor discharging, right? IC positive, here it is IC is positive. So here capacitor is charging. Next, again, you can check IC negative here. Okay. So it is like t plus this instant, na? Means in between t and t plus t on. In between t and t plus t on. So in between t and t plus t on, I have taken this instant. It is discharges and again charges. Okay. So now, yes, let me indicate it as so capacitor voltage will vary between these 2 points. Actually. Okay. So and this is nothing but your delta VC. Difference between this value and this value, or maximum value minus minimum value, means this is difference. This difference is nothing but your delta VC. That is a ripple in capacitor voltage. We are having the two terms. One is a ripple in inductor current. Second one is ripple in capacitor voltage. Okay, ripple in capacitor voltage and ripple in inductor current means this one, delta IL, and this is a delta VC. Okay, we are going to derive the expressions for delta VC as well as delta IL also. Okay, so this is the waveform of VC, waveform of IL, I0 and IC, right? Similarly, we can draw the waveform of ID, right? ISW, IS and so on. Okay, so let me draw the waveform of IS. Okay, let me draw the waveform of IS. Yes, IS waveform. Zero to T on to T, and T to T plus T on. Please don't lose the concentration, right? So 0 to T on switch is on state. What is the IS? Come on, recall the circuitry. Between T is equal to 0 to T on switch is in a on state. When switch is in a on state, IS and IL both are same or different. Come on. We already written it. Yes, when switch is in a on state, you can check. When switch is in a on state, yes, IS and IL both are same or different? Both are same, na? Yes or no, right? So we are having the IL waveform. So accordingly, can I draw the waveform of, yes, if we are having this IL waveform, so can I draw the waveform of ISW or IS first? Yes, same. Okay. So it is same I1 to I2, it is increasing. So waveform is it I1 to I2. It is increasing from I1 to I2. This is the I1, this is the I2. Okay. When T on to T means switch is in a off state. When switch is in a off state, what is the switch current? Sorry, what is the source current? You can check the circuit. When switch is in a off state, when switch is in a off state. Yes, switch is in a off state. What is the source current? Source current is 0, na? Right? So how will the waveform? The source current should be 0. So it is like this. So we are having the waveform for the source current. It should be like this. So it is changing from I1 to I2 when switch is in on state, and again it is a 0. Again the same pattern repeats. Okay, again it is a I1 to I2. I1 to I2. This is the waveform of IS. Now my question is, how is the waveform of ISW, switch current? Come on. Switch current waveform. T on T and T plus T on. Whether the switch current waveform and source current waveform both are same or different? Both are same, na? Right? Both are same, right? Yes, good. So here the waveform will be same as that of your IS. So this type of waveform we get it. So this is your I1. Here it is I2. Okay. So again, can I write it as this is the same as that of your IL, na? Same as that of your IL. Okay, same as that of the IL. Next, this is IS and ISW. Can we draw the waveform of ID, diode current? Come on. Diode current. T on T plus T on. When switch is in on state, what is the diode? Diode is a reverse bias mode, na? Diode is in a off state, right? So when switch is in a, yes, okay. So when switch is in a on state, the diode current is 0 because diode was filling the reverse voltage and it was in off state. And when switch was in a on state, what is ID? ID is the same as that of the inductor current. So inductor current is like a decreasing, na? It was. So that's why it will be like this. So we'll be getting this type of waveform for ID. It is changing from IT to I2 to I1. I2 to I1. And this is your IL. Same as that of the IL, na? Same as that of IL. Only for this period I am saying same as that of IL. Okay. So IS waveform, ISW waveform, and ID waveform. Okay. Already we have written these things when switch is in a on state and when switch is in a off state. Okay. Same things. Yes, Vishnu, do you want to say something?
So nothing, sir.
Nothing. Okay.
Sir, here we start from I1 to I2, not from 0, sir. Why we not?
Because in steady state, because in I0, when we start the 0 at a very first cycle. In a steady state, actually the thing is this is a DC to DC converter, na?
Yes, sir.
We require constant voltage output side.
Yeah.
And our circuit should give the constant current also.
Yes.
Right? So for that we have connected the inductor in series with the load.
Yes.
Right? And if for all the cycles, that like from 0 to T, suppose for every time, if I selected the value of inductor, like it is changing, inductor current is changing from 0 to the maximum, and again it is reaching to the 0 value, whether it will affect, okay, on your average value of the circuit current or your output current. Yes, it will affect. We will discuss it, because at the end we are having the just continuous conduction case also. Okay, this is like your continuous conduction, this is like your continuous conduction, right?
Yeah, I think if it current is 0, then no use of that circuit in
No,
second
no, it
cycle.
is not like that. It is not like that. Okay, we are going to discuss. Please have some patience. Okay, so yes, only try to understand how to draw the waveforms here. Okay, so
Okay.
yes,
Thank
yes.
you, sir.
Remaining questions I will answer at the end of the session. Okay, so
Okay.
yes. So IS, ISW, ID waveforms we draw. At the same time, IL, I0 and IC and as well as the VC waveform we have drawn. Yes or no? Right? Next, now, yes, one by one, now let us follow the steps. Okay. So after this, we need to find the peak to peak inductor current, that is a delta IL. Okay, peak to peak inductor current, that is a delta IL. Next step is volt second balance equation we return, ampere second we return, right? Ripple in inductor current. So fifth one, ripple in inductor current. Ripple in inductor current, that is a delta IL. So how to find the value of this delta IL, let us discuss. Okay, so here we need to apply the KVL to the circuit either during on time of the switch or during off time of the switch. In both the ways you will be getting the same answer. Okay, in both the ways you will be getting the same answer. Okay, so let me first write when switch is on. When switch is on. Okay, so when switch is in an on state, how the circuit we are having? We are having the circuit like it is like a switch is in an on state, diode open circuit. Here it is the inductor na. Here it is a capacitor, and here it is a R. So this type of circuit we already discussed. This is a Vs, right? This voltage is like a VL. This is your IL, inductor L, capacitor C, R, V0 and I0. Now, yes, when switch is in an on state, what is the VL expression we wrote? We wrote VL is equal to, it is like a V0. Yes, you can apply KVL plus Vs minus VL na. KVL to loop plus Vs minus VL minus V0 is equal to 0, right? So from this I can write, therefore VL is equal to Vs minus V0. Vs minus V0. Now you can check here. VL means what? Voltage across inductor. It is equal to L into DIL by dt na. So can I write it as L into DIL by dt, which is equal to Vs minus V0. What is the V0 expression? This is the buck converter. We have derived V0 is D into Vs na. D into Vs. Yes or no? Right? So I am replacing this V0 with a D into Vs. Further, I can write it as L into DIL means what? Change in the inductor current. So recall the inductor current waveform during when switch is in an on state, that is T is equal to 0 to T on. Okay. So T is equal to like a 0 to T on. During this state, you can check how the inductor current is changing. Inductor current is changing from I1 to I2 na. Yes or no? Right? So what is the change in the inductor current? It is a I2 minus I1. Right? I2 minus I1. So it is a I2 minus I1. Divided by dt means what? Change in the time. What is the change in time? T1 minus 0. T1 minus 0 is equal to Vs into, we can write it as a 1 minus duty cycle D. Right? So further I can write it as, therefore I2 minus I1 means what? That is a delta IL na. That is a ripple in inductor current we indicated. You can check the IL waveform. Delta IL means what? I2 minus I1. Okay. So I can write it as a L into delta IL divided by T on means dt is equal to Vs into 1 minus duty cycle D. Next, so further we can write it as, therefore delta IL is equal to Vs into 1 minus D into dt. Okay, Vs into 1 minus D into dt divided by L. Okay, is this clear? So or further we can write it as is equal to Vs or D into 1 minus D into 1 minus D into Vs divided by F into L. F into L. This is a delta IL. That is expression for ripple in inductor current, delta IL. Please try to understand here. So in order to minimize the delta IL means what? Are you getting the point? Minimize the delta IL. Here we are having the IL waveform. If we are interested in minimizing the delta IL, if delta IL is minimized means what? Here I2 and I1, the difference will be decreasing now. I2 and I1 difference will be decreasing. Means what? Nearly will be getting the IL is a constant current, right? IL is a constant current. Okay, and if your IL is constant, obviously it will help for getting the constant current in the load, right? So here you can check if we are having a, if we want to minimize the delta IL, what is the requirement? The inductor value should be high na. Delta IL will be minimum when inductor is maximum, right? So that's why always keep it in mind. Higher the value of inductor, more constant current you will be getting. More constant current means the delta IL will be very less na. Yes or no, right? So here, let me write it as to reduce ripple in inductor current. Ripple in inductor current, to reduce ripple in inductor current IL. Okay, L should be high, inductor value should be high. And one more thing, what we can do, you can check the frequencies also here na. If I increase the switching frequency, what will happen? If switching frequency increases, delta IL will decrease na. How the switching frequency or increase in the switching frequency will cause the decrease in the delta IL? Because you can check, switching frequency increases means your total time T decreases na. We are having this waveform. Switching frequency increases means the total time T decreases. Total time T decreases means your T on decreases, T off also decreases na, right? So that's why it is like inductor is getting a lesser time to store the energy and to lesser time to release the energy as well. So that's why this difference I2 and I1, this difference go on decreasing. Are you getting the point? Okay. So they have asked the questions, right? Theoretical, right? So in order to decrease the delta IL, either your FL should be high and at this, yes, switching frequency also high. We can reduce the delta IL by increasing the switching frequency, by increasing the value of L also. Okay. So, and L should be high and F is also high, right? F is also high. F required is also high. F required is also high. Now, if you check in these circuits, which devices we are using, which devices we are using as a switch, whether we are preferring the SCR? No, because SCR is having a limitation of like your switching frequency, na, right? So that's why we are generally preferring which devices? IGBT, BJT, MOSFET, etc. Okay, so because they are having the high switching frequency compared to that of your SCR, right? So this is the delta IL, right? Delta IL. Next, after the delta IL, we are having the IL max and IL min expression. IL max and IL min. So let me put the heading IL max. IL max means maximum value of inductor current. Maximum inductor current. Maximum inductor current, right? In our case, IL max means I2 na, we consider it as a I2. IL max is a I2. So here, yes, we are having a IL waveform this type. Okay. So now here, can I write this value I2 is equal to IL average plus delta IL by 2? Please listen to what I am saying. Here, can I write I2 is equal to IL average means this value plus delta IL by 2. Delta IL by 2 means only, yes, 50% of this delta IL. So IL average means this value, right? It is like this point IL average. If I want I2 value, so in this value I need to write add delta IL by 2. Okay, so I can write it as a I2 is equal to IL average plus delta IL by 2. Let me write as capital delta IL. Okay, delta IL by 2. Right? So again, IL average means we are having I0 again, right? IL average and I0 average both are same. We discussed earlier. Okay. So which can be written as I0 plus delta IL by 2. Delta IL by 2. This is your IL max. Similarly, can we write IL mean? Minimum value of inductor current. Minimum inductor current. Minimum inductor current. Yes, IL mean is equal to I1 is equal to, yes, now can anyone? We have written the I2 in the same way. Can we write the I1? It is like IL average minus delta IL by 2, na? Yes or no? IL average minus delta IL by 2, right? So it is IL average minus delta IL by 2, which is equal to I0 minus delta IL divided by 2. Okay. Further, we can write IL average. IL average is I0, right? No problem. But at the same time, we can write I0, IL average in terms of I1 and I2 also. In terms of I1 and I2 also. Okay. How? It is a I1 plus I2 divided by 2. You can check here. This is a linear waveform we are having, right? So we discussed, suppose this is a 1 ampere, this is 3 ampere. So, and if this is linearly increasing, what is the average? It is a 2 ampere, na? Suppose we are having a current waveform which is changing from 1 ampere to the 3 ampere. It is a linearly changing. So what is the average value? It is a 2 ampere. How we have calculated it as 2 ampere? It is like a 1 plus 3 divided by 2, na? Right? So that is lower limit, upper limit, lower limit plus upper limit divided by 2. So same way I1 plus I2 divided by 2. So here also I1 plus I2 by 2, right? So this is your IL average. This is the IL average. Okay. So we have written IL max, IL mean, IL average. Okay. IL average. Next one is the source current average value. Average value of source current. Average source current. So how to find the average source current? Let us discuss. We are having the IS waveform. We are already drawn. 0, T on, T, and again T2, T plus T1, right? So we are having the waveform like this, na? IS is same as of the IL during 0 to T on, and again T1 to T, it is a constant, it means 0, and again same. So this is like your I1, this is like your I2, right? I want to find the average value of this waveform. So either you can find by equating the input power is equal to output power, because in the circuit, if you check, in the circuit we are having a supply side, and at the output side we are having the load. Okay. So input power is equal to output power, you can equate, because other elements whatever we are having in the circuit, just like inductor, diode, switch, capacitor, whether they consume the real power, no, right? So I can write input power is equal to output power. Output power. So what is the input side? DC. What is the output side? It is also DC, na? So can I write it as IS? This IS is nothing but IS average only. Okay. IS into VS is equal to V0 into I0. Right? So further we can write, therefore IS is equal to V0 into I0 divided by VS. This can be written as V0 is, this is a buck converter. V0 is D into VS, na? D into VS into I0 divided by VS. So VS will get cancelled out. It is equal to D into I0. This is the IS. Okay. Now you can check. We assume the I0 is constant. So this duty cycle D into the constant value means what? It is again constant value, no? So that's why this IS is nothing but your IS average. This IS is nothing but IS average. This is the one way, right, by which we can find the IS average, or how we can find by using this expression also, by using this waveform also. Okay. So for that, what I am going to do, I am simply going to approximate this waveform. Okay. Because it is a linearly changing from I1 to I2. Further, can I draw the IS waveform like this? 0, T on, T. I am drawing the waveform like this. Means whatever the portion was there, that is changing, right? I1 to I2, it was increasing linearly. Okay. I am approximating this. I am approximating this as an average of these average of this one. What is the average of this I1 to I2 linearly increasing average will be I1 plus I2 by 2 now. It is again same as that of your IL average. So can I write this is equal to your IL average? Yes or no? Which is equal to I0 average, which is equal to constant current I0. Now you can find here IS average for this waveform. You'll be getting this value only D into I0. You can check. IS average is equal to 1 by T integration from 0 to T on. It is a I0 into dt. Na? This can be written as is equal to I0 into T on by T. So it is equal to D into I0. Yes or no? You can find in both the ways, you'll be getting the same answer. Okay. Either you can equate input power is equal to output power, or you can draw the waveform of this IS. This waveform we have already discussed how to draw. And after that, I am approximating this. Okay. 0 to T on pulse like this. Okay. So this is your average source current. Average source current. Next. Now, can we find the average switch current? Average switch current. Yes. Yes, average value of switch current. Come on. Average switch current and average source current both will be same or different? Average switch current and average source current both will be same or different? Both will be same, na? Yes or no? Because we are having the waveform same for IS, W and IS. This is time T, 0, T on and T, na? So waveform is like this. This is I1, this is I2. Okay. So again, ISW average is equal to IS average is equal to duty cycle D into I0. Duty cycle D into I0. Right? Next, average diode current. Average diode current. Average diode current. Yes. How will be the diode current waveform? This is ID. Zero to T on to T. Okay. 0 to T on diode current is 0. T on to T diode current is same as that of the inductor current, but T on to T inductor current is like this, na? It should be decreasing. This is I2. This is I1, na? Right? Same as that of the inductor current. Now, ID average if I want to find. So simply I am approximating this waveform in the way we approximated for the source current, na? You can check it is I2 to I1 linearly decreasing, na? So average will be like I1 plus I2 by 2. I1 plus I2 by 2 means IL average only. Okay. So it is like this. This is a T on, this is a T. If you don't want to approximate, what we're supposed to do? We need to find the expression of this waveform, right? It is a decreasing, na? We can find the expression of this waveform, and after that we need to find the average value. Okay. Next, so this is your IL average. So therefore ID average, let me write ID average. Average value of diode current is equal to 1 by T integration from T on to T. What is value? IL average into dt. IL average means it is I0 only, na? I0 average, which is equal to capital I0. So I'm writing it as I0 into or I0 by T into T minus T on, na? So this can be written as 1 minus D. It is what? T by T minus T on by T. That is 1 minus D into I0. This is your ID average. This is the ID average, right? Average value of diode current. Okay. So next point is ripple in capacitor voltage or output voltage. So ripple in capacitor voltage. or I am saying output voltage. As capacitor is connected across the load, na, so we can say that load voltage is equal to capacitor voltage. Okay, so ripple in capacitor voltage or output voltage. So for that, that is delta VC or delta V0. Okay, delta VC, which is equal to delta V0. Now we are going to write the expression for this one. Okay, so how to write the expression? Please understand. So for that, we need to refer the waveform of VC and a waveform of IC. We need to refer the waveform of VC and waveform of IC. Okay, so let me write before that. Can I write, as we know, C is equal to Q by V. So from this, I can write it as a V is equal to Q by C. So therefore, can I write delta V instead of V now? Can I put delta VC is equal to delta Q divided by C, because C value is constant, na? Right? So can I write delta VC is equal to delta Q by C? What this delta Q indicates? Delta Q indicates, yes, the change in the charge. Okay, that is charge stored by the capacitor or charge, yes, or discharged by the capacitor. Okay, so now for that, please check the wave. Means we need to find, in order to find the delta VC, we need to find the delta Q actually. How to find the delta Q? Let us understand. Okay, so here we're having the waveform of, yes, VC waveform is like this, right? So delta VC means what? This peak value minus this minimum value. The difference between the two is nothing but delta VC, na? So you can check from this point. This point is like a T on by 2. We indicated. Okay, and this type, this point is like a T off by 2, na? Is this fully this was it is like a T off by 2. Okay, so we indicated this point and this point on IC also, right? We'll discuss. So from T on by 2 till this instant is like capacitor is like a charging. So capacitor voltage is changing from minimum value to the maximum value. So difference between these two voltages means delta VC. So now you can check corresponding to these 2 points. Corresponding to these 2 points, what is the IC we are having? So we are having a IC here. So you can check this point is a T on, na? Here it is a T on, where this point is a T on. So T on means the same point here. So before T on we are having 1 point, after T on we are having 1 point. Between these 2 points, the capacitor is charging, na? Okay, so you can check here. This point is like, here it is. Okay, and after T on means this point we are having. Okay, so now corresponding to this point, actually between these 2 points, the capacitor voltage is changing from minimum to the maximum. So if I want to find the change in the capacitor voltage, na, corresponding to these 2 points, so for that I have written it is equal to delta Q divided by C. Delta Q we need to find. So if you check, can I say that the area under this triangle, right? Area of this triangle will give me the delta Q. You can check, this is a IC and this is a time. Okay, delta Q means what? Yes, we know I is equal to dq by dt, na? Okay, so it is like current into time is nothing but your charge, na? Okay, so here same thing, area under this triangle will give the delta Q. Let me write it as a delta Q, because it is 1 by 2 into IC, that is peak value of this IC, into this time, na? So that will be your delta Q, right? So delta Q I can write it as area under this triangle. So which is equal to, let me write it as 1 by 2 into, what is this height? It is a delta IL by 2, na? And this time is T on by 2 plus T off by 2 means T by 2. Okay, so let me write it as delta Q. Please try to understand this. Therefore, delta VC is equal to delta Q means area under the triangle, that is a 1 by 2 into delta IL by 2 into, yes, we are having a that T by 2 divided by C, na? Divided by C. So further can I write it as therefore delta VC, therefore change in the capacitor voltage delta VC is equal to 1 by 8C into T into delta IL. Delta IL into T divided by, yes, it is like a 8C divided by 8C. Yes or no, right? Delta IL into T divided by 1 by 8C, that is 8C. Now what is delta IL? We have already written the delta IL. Please check that delta IL we need to put here. That delta IL we need to put here. Okay. So what is the delta IL we have written? Yes, you can check here. Delta IL Yes, d into 1 minus d into Vs, okay, upon FL, d into 1 minus d into Vs by FL, okay. So d into 1 minus d into Vs into T, this as it is, divided by FL, na? So 8 into F into L into C. This C8 as it is, I have added F into L, okay, divided by FL, d1 minus d Vs by FL, okay. Now you can check, can I replace this? Can I replace this F with 1 by T? So that will become your T square here, right? That will become your T square. So it is equal to d into 1 minus d into Vs into T square divided by 8 into LC. This is your delta Vc, okay, delta Vc. Either you can write in terms of T square or you can write it in terms of F square also, right? Doesn't matter. So also delta Vc is equal to d into 1 minus d into Vs divided by 8 into LC into F square. What this F indicates? Whether it is a supply frequency. What this F indicates? Whether it is a supply frequency. Yes, it is a switching frequency, right? It is a switching frequency because supply frequency we don't have. We have a DC, na? Right? We're having a DC supply. So that's why we don't have a supply frequency. So it is d into 1 minus d into Vs upon 8 into LC into F square.
Sir,
right?
I have a doubt.
Now, yes, please.
Sir, that any method we can prove that this time is T on by 2 and T off by 2, sir.
What? Please repeat.
Sir, the time at which this IC current becoming 0 to where IC is becoming peak is T on by 2. So that's what you mentioned in the diagram.
Time at which
that current IC, capacitor current becomes 0 to the point where capacitor currents become del IL by 2.
Okay. Means corresponding to that, yes, you are saying here.
In that waveform, sir.
This one.
Yes, sir. This T on by 2, how can we see?
Yes. You can check here. This is constant.
Okay, sir.
This is linear.
Yes, sir.
And if during this period, if it's changing from I1 to I2,
okay.
So it is exactly passing through, it is having the same value.
Okay.
Can I say that at the center point of the T on?
Okay, so intuitively you can, okay.
Yes or no? Because it is a linear and this one is constant. And one more thing, this IL average is nothing but what? Your I1 plus I2 by 2, na?
Okay.
So that's why it is passing through exactly at exact T on by 2, it is having the equal value.
Okay, sir.
So that's why it is getting 0 here. Where?
Okay.
Right?
Yes, sir. All right, sir. Thank you, sir.
Yes. Okay. So now this is your delta Vc. Now here also you can check delta Vc means what? Change in the capacitor voltage. Okay. And this delta Vc is again equal to what? Your delta V0 now. Because capacitor is connected across the load. And ideally what we require? Ideally we require a constant load voltage, na? Constant output. So if I want to minimize this delta Vc, what we need to do? If we want to minimize this delta Vc, yes, what we need to do? We need to increase the switching frequency. We need to increase the value of capacitor also. Yes or no? Right? Is this clear? So more the capacitor value, yes, lower will be your delta Vc. We know capacitor is the element which opposes the change in the voltage, na? Right? So higher the capacitor value, higher will be the opposition offered by the capacitor to change in the voltage across it. So that's why more constant voltage will be getting. Is this clear? Right? So it is d into 1 minus d into Vs upon 8 into LC into F square. Okay, 8 into LC into F square. Okay, so right. So I will answer all your questions at the end of the session, right? Okay, so because we need to cover a lot of things, right? So this is the Vc which is equal to delta V0. That is the ripple in the capacitor voltage, which is equal to ripple in a load voltage also. Right? So this expression is important. Delta IL expression is also important, right? So next point is D at which the ripple is maximum. Yes, D, duty cycle D at which the ripple is maximum. So let me write duty cycle D at which ripple is maximum, at which ripple is maximum. Ripple is maximum. Ripple means what? The difference between maximum value and minimum value, that is nothing but the ripple, that's it. Okay, so duty cycle D at which the ripple is maximum. Okay, so let us first find for delta IL. Okay, duty cycle for maximum delta IL. So duty cycle for maximum delta IL, maximum delta IL. Okay, so now we are going to find the value of duty cycle at which the delta IL is maximum. Delta IL is maximum, right? So for this, we are going to take the help of maxima theorem. We are going to take the help of maxima theorem, right? So first of all, let me write the delta IL expression as it is. We know delta IL here also we have replaced, right? Delta IL means what? This you can check D into 1 minus D into Vs, okay, upon F into L, na, right? Upon F into L. Okay, so let me write it as D into 1 minus D into Vs upon F into L, right? Upon F into L. This expression we are having for delta IL. Now, with according to the maxima theorem, right? Can I take the differentiation with respect to duty cycle of this delta IL and can I equate it to 0 in order to get the value of D at which the ripple is maximum? So if I want to differentiate this term, it is like a D by dd of, you can check D into, yes, D into 1 minus D into Vs upon F into L. This should be equal to 0, right? So now you can check FL is constant, Vs is constant. So can we take it outside? If you take it outside and again 0 divided by that term, that will be 0 only. Okay, so only thing is we'll be having D by dd of D into 1 minus D. D by dd of D into 1 minus D is equal to 0. So therefore, can I write it is D minus D square. So it is like a 1 minus 2D is equal to 0. So what is the D? D is equal to 1 by 2, which is equal to 0.5. The meaning is, if a duty cycle is 0.5, your delta IL will be maximum. Your delta IL will be maximum. Are you getting the point? They have asked the question, the duty cycle corresponding to the maximum delta IL in buck converter is, it is a 0.5. It is a 0.5, right? So next, similarly, can we find the duty cycle for maximum delta VC? Yes, duty cycle for maximum delta VC. Duty cycle for maximum delta VC. Maximum delta VC. Or you can say delta V0. Okay. Delta V0. So we are having a delta VC expression or delta V0 expression. What is that? Here it is. D into 1 minus D into Vs upon 8 LCF square. D into 1 minus D into Vs upon 8 into FC into 8 F square into LC, na? Check. 8 LC F square, correct? 8 LC. So we need to put differentiated D by dt of delta VC and we need to equate it to 0, right? Next, so therefore we can write it as a D by dd of this term as it is, D into 1 minus D into Vs upon 8 into LC into F square is equal to 0. So you can check Vs constant, 8 LC F square all are constant. So it is like D by dd of D into 1 minus D. Equate it to 0. So therefore it is like a 1 minus 2D again, na, is equal to 0. So therefore D is equal to 0.5. So when duty cycle D is equal to 0.5, your delta VC will be maximum. Delta VC will be maximum, right? So this is the duty cycle at which the delta VC is maximum, and similarly for delta IL is maximum. Okay, so means simple, when duty cycle is 0.5, we will be getting maximum delta IL, maximum delta VC also. Next, critical inductance and critical capacitance. Okay, critical inductance and critical capacitance. So first, critical inductance. Let us understand what is the critical inductance first. Yes. Try to understand it. Yes. Let us indicate it as LCR. Okay, or L critical you can write. Okay, L critical. So what it indicates? Till now, whatever the circuit operation that is for buck converter we discussed, it was by considering the IL is a continuous, by considering the IL is a continuous only. Okay, so critical inductance means what? You can check whether our IL waveform depends on the value of L. Obviously, as we know, L increases, opposition offered by the inductor to change in the current increases, definitely your slope of the IL waveform will change. Yes or no, right? So now critical inductance means what? It is the value of inductance at which the inductor current is just continuous. Inductor current is just continuous. Okay, so please let me write first. So critical inductance is a value of inductor at which inductor current is just continuous. Inductor current is a just continuous. So what is the just continuous? Let us understand. Okay, what is the just continuous? Let us understand. So just continuous means it is like a boundary between continuous and discontinuous conduction. Just continuous means a boundary between continuous and discontinuous conduction. Okay, so let me write just continuous is a boundary between continuous and discontinuous conduction. Continuous and discontinuous conduction. Right? Boundary between continuous and discontinuous conduction, right? So now let us understand at a boundary or at just continuous, how will the waveform of your IL? Okay, let us understand. So let me draw first the waveform of IL. Whatever we discussed, for that case, the waveform of IL, it was like this: 0 to T1, T1 to T, and T to T plus T1. So IL was during 0 to T1, it was increasing, na? That is I1 to I2. This is I1, this is I2. And when switch is in off state, it is like a IL was decreasing. And again, it is increasing. Okay, so we're having a IL which is varying between I1 and I2. Means for all time t, the value of IL is a non-zero only, na? So that's why it is a continuous conduction. This is your continuous conduction or continuous IL. Continuous IL, right? This is the continuous IL. Next, let me draw the waveform of just continuous. Okay, for the just continuous case. As I said, it is a boundary between, right, continuous and discontinuous. Okay, so means that from 0 it will reach the peak value during T on. Inductor stores energy, so definitely your IL will be increasing. During T on to T, switch is in an off state, inductor current decreases, and at this instant it will reach the 0 value. And again, when it reaches the 0 value, at the same instant the next on time starts. So again the inductor current increase. This is like your just continuous. This is the just continuous IL. Just continuous IL. That is the boundary between discontinuous and continuous. Okay, and next, what about the discontinuous? Discontinuous means like this. Yes, just discontinuous. From 0 it increases, reaches the peak value, and after that it will decrease, and it is having some 0 interval. Okay, and after some time again the next on time starts, right, and the same repeats. It is like a T on, this is like a total time T, and this is like a T plus T on. right? This waveform is discontinuous. Discontinuous. Are you getting the point? Difference between the three waveforms, right? First one is the IL is a continuous. Second one is the IL is a just continuous, and third one is the IL is a discontinuous. The discontinuous means what is happening during 0 to T1, inductor is storing the energy, and during T1 to T, when switch is in off state, na, yes, before the next on time, inductor energy becoming 0. So you can check from this point to this point, it is like a inductor current is 0. Are you getting the point? So that's why it's a discontinuous. Okay. Now our task is here. L critical means what? Yes, our task is to find the value of inductor corresponding to this just continuous conduction. Once I get that value, then can I say that if the value of inductor is greater than the L critical, then our IL is continuous IL is a continuous. If the value of L is less than L critical, then the conduction will be discontinuous. Because the thing is, higher the value of inductor, higher will be the energy stored by the inductor, higher will be the time taken by the inductor to release the energy. Yes or no, right? So continuous conduction means it is like a value of inductor is high. Just continuous means value of inductor is equal to L critical. And discontinuous means value of inductor is less than the L critical. That is your discontinuous. Okay. So now our task is to find the value of inductor corresponding to this just continuous conduction, right? So now let us discuss how to find, right? So here, yes. So for the just continuous case, you can check. This is your I2, yes or no? That is the maximum current of the maximum IL, right? That is the I2. Here, what is the minimum value of inductor current? It is a 0, na? It is starting from 0. So can I say that I1 is equal to 0 here? So in this case, in a continuous case, I1 and I2 both are non-zero. In the just continuous case, I1 is 0, I2 is a positive, right? I2 is a positive, that is a non-zero. Okay. So now can I say that delta IL? Can I say that the delta IL means difference between two? Yes or no? Delta IL means difference between the two, na? Right? That is maximum value minus minimum value, that is the delta IL. Okay. So can I write for just continuous conduction, delta IL is equal to I2 minus 0, that is equal to I2 only. Okay. So let me write for, yes, for just continuous conduction, yes, for just continuous conduction, delta IL is equal to I2 minus 0, which is equal to I2, right? Now for the just continuous conduction, what is the IL average? Can anyone? IL average? IL average means average value of the, yes, inductor current. You can check it is changing from 0 to peak value, and again it is decreasing from peak value to the 0. So can I say that IL average means it is like I1 plus I2 by 2, na? We know this is your IL average. We already written IL average means I1 plus I2 by 2. Okay. So therefore IL average is equal to I1 plus I2 divided by 2. But what is I1? I1 is 0 plus I2 by 2. So can I write it as it is equal to I2 by 2 only, which is equal to I2 means what? It is a delta IL. So we can write it as a delta IL divided by 2. So IL average is equal to delta IL by 2, right? IL average is equal to delta IL by 2. Is this clear? Okay. So this is your IL average. Now we know, yes, for continuous conduction, now important thing, just continuous is nothing but continuous only. Please be careful. Huh? Just continuous conduction is like a continuous conduction only, because it is starting from 0, it reaches the peak value. From peak value, it is decreasing, and at the same instant, again the next on time is starting now. So it is, we cannot say that here the current is a discontinuous. No, here the current is continuous only. It is not a discontinuous. Right? So here, now you can check here. IL average means what? We have written it is I0 average. Okay. So I can write it as I0 average is equal to delta IL by 2. It is equal to delta IL by 2. I0 average means again it is a capital I0, which is equal to delta IL by 2. What is delta IL expression we have written? Delta IL we are having the expression. Yes, you can check. This is a delta IL, na? D into 1 minus D into Vs upon FL. Okay, D into 1 minus D into Vs upon FL. So let me write therefore, yeah, therefore, which is equal to D into 1 minus D into Vs upon F into L. And these two as it is, right? We are having divided by 2. So it is a 2FL. Please check delta IL expression. Yes. D into 1 minus D into Vs by FL. Same expression I have written here, right? Again, this side we are having a I0, na? We are having a I0, right? So I can write I0 means what? Load is a resistive we considered. So can I write I0 is equal to V0 by R? So it is equal to V0 by R, right? So therefore, can we write it as, again, V0, can we replace V0 with a D into Vs? It is a buck converter, na? So it is a D into Vs divided by R, which is equal to D into 1 minus D into Vs upon 2 into FL. Okay. Now, one more thing. Now, okay. So here you can check dVs, this dVs, dVs, it will get cancelled out. Okay. So it is like we can write it as a 1 by R is equal to 1 minus D upon 2 into FL, upon 2 into FL. Okay. So now from this, yes, we can write, if I want the L critical value, na, if I want the L critical, okay, so I can write it as, therefore L critical is equal to 1 minus D into R upon 2 into F. This is your L critical value. If I want the R critical means, please try to understand. For the given value of inductor, if I want to select the value of resistor, yes, in order that your IL is just continuous, okay, then that will be your R critical. Okay, so also let me write R critical. Also from this only I can write R critical is equal to, this can be written as 2 into FL divided by 1 minus D. 2 into FL divided by 1 minus D. Okay, this is your R critical. Also, we can write the D critical also. Right? But not required. Okay, so is this clear? So this is your L critical expression. This is your R critical expression. Okay, next. So how we have written, please try to understand. For just continuous, I have drawn the waveform. From that, we have written these two expressions. I0 is delta IL by 2 we got, and after that, here we are having simplified. Okay. Next, last one, critical capacitance. Critical capacitance Yes. Critical capacitance means C critical. That is the value of C, that is value of capacitor corresponding to your VC is a just continuous. Okay, VC waveform is a just continuous. Okay, you can check VC, whatever we discussed earlier, it was like discharging, charging, discharging, charging, and for all the time it is a non-zero, na? So that was a continuous. But in this case, if we want like that, okay, that is a it is discharging from non-zero value to the zero value, and again charges from 0 to the peak value. Okay, so that will be your just continuous type thing. Okay, so now in the same way here, whatever I have written, yes, IL average is equal to delta IL by 2. Similarly, I can write VC average is equal to delta VC by 2. VC average is equal to delta VC by, same thing I have written, because IL average means this type of expression, this type of waveform we're having, na? So for VC, if I want to draw for the just continuous, it is like it is discharging, reaches 0, and again charges from same point. Okay, so it is delta VC by 2, VC average. Okay, so VC average means your V0 average only is equal to delta VC by 2. Again, we're having the expression for delta VC. You can check delta VC expression we have written. Yes, D into 1 minus D into Vs upon 8 F square into LC. Okay, so which is equal to D into 1 minus D into Vs upon 8 into F square into LC, right? So this is your V0 average. But what is the V0? This is a buck converter, which is equal to D into Vs, na? So it is a D into Vs. So can I write it as D, D, Vs, Vs cancel out. Okay, so therefore I can write C critical. Therefore C critical is equal to 1 minus D upon 8 into F square into L, right? 8 into F square into L. Sorry, one more thing, into 2 into right? Correct. So this should be the 16. This should be the 16. Right? 2 into 8, 16. This is your C critical. Is this clear? 1 minus D upon 16 F square into L. Is this clear? Okay. So this is the critical capacitance value. Critical capacitance, right? Okay. So we'll take a break here.
Hello, sir.
Yes, please. Abhijit.
Sir, in R critical formula, there is 2FL critical or only normal L?
No, normal L.
Okay, okay.
Are you getting the point? If means the meaning is for this expression, the meaning is suppose we have already placed the inductor in the circuit.
Okay.
Then at which value of load resistor your IL become just continuous. Okay.
Okay, sir.
Right. So here it is R critical. Then in that case it is a L only. Right. If it is a
Okay,
L
sir, got
critical,
it.
then in that case here it is R only. Right. Okay. Yes. Okay. So we'll take a break here and we will start at 7:30. Okay, 7:30. Okay. So now let us discuss the maximum value of inductor current ripple and maximum value of capacitor voltage ripple. Okay, so yes, maximum value of inductor current ripple. I'm saying inductor current ripple. Inductor current ripple. So here that is delta IL max, right? We are going to write. So just now before the break, yes, we have written the maximum value of inductor ripple will occur at d is equal to 0.5. Yes or no? D is equal to 0.5. So from this, can I write delta IL max is equal to delta IL at d is equal to 0.5? Yes or no? D is equal to 0.5, right? So let me simply put d is equal to 0.5 in order to get the maximum value of delta IL max. Okay, so maximum value of delta IL. So delta IL we are having, yes, here it is the expression of delta IL. We have written d into 1 minus d into Vs upon 2FL. Okay, d into 1 minus d into Vs upon 2 into FL at d is equal to 0.5. We need to write. Okay, so simply put here d is equal to 0.5. So it is equal to 0.5 into 1 minus 0.5. So it is a 0.5 into Vs upon 2 into FL, right? So 0.5, it is a 0.25. So this can be written as 0.25. We can write it as 1 by 4. Okay, so this is equal to, yes, Vs upon 8 into FL, no? Right? So this is your delta IL max. Vs upon 8 FL. Is this clear? Right? Maximum value of ripple in inductor current. Similarly, can we find maximum value of capacitor voltage ripple? Right? So maximum value of capacitor voltage ripple. Capacitor voltage ripple or ripple in capacitor voltage, you can say. Yes. So delta VC max. Again, it is equal to delta VC at d is equal to, we have written na, d is equal to 0.5. This delta VC is maximum. So at d is equal to 0.5. Means in the delta VC expression, we need to put d is equal to 0.5, right? We need to put d is equal to 0.5, right? Yes, what you are saying? Yes.
Sir, in delta IL expression, whether 2 will come in the denominator, sir, extra.
That okay. Yes, correct. That is divided by, sorry, only FL, right? Thank you. Dash 2 will not be there, right? So it is a 4 only, right? Yes, by 4. Thank you. So next, delta VC at d is equal to 0.5. So you can check delta VC expression we are having. It is d into 1 minus d into Vs, okay, upon 8 into F square into LC. D into 1 minus d into Vs upon 8 into F square into LC. So again, put here d is equal to 0.5. 0.5 into Vs divided by 8 into F square into LC. So this can be written as Vs upon 32 into F square into LC, right? This is your delta VC max. Maximum value of ripple in capacitor voltage. Okay, maximum value of ripple in capacitor voltage, right? Next. So this is what we discussed for continuous conduction and as long as your critical conduction is considered. But suppose if the conduction is discontinuous, then what will happen? Let us discuss. Okay, if the conduction is a discontinuous, I am saying. Okay, so next, let me put that in. If conduction is discontinuous, if conduction is discontinuous, so the conduction is discontinuous means, suppose we are having a IL waveform is like this, 0 to t on, or let me write it as in terms of dt. Write me it in terms of dt. This is like your total time t, and suppose this is a beta t. This is like a beta t. Okay, so during 0 to dt, which is in a on state, inductor go on storing the energy na, so IL will increase from 0. This is a discontinuous conduction we are going to discuss. It will reach the maximum value. Let me write it as a max. After that, dt to t, the switch is in an off state. But as this is the discontinuous conduction, consider the inductor is releasing the energy only till beta t. And during beta t to t, it is like a circuit will be at the rest position. After t, again the same will repeat. Please try to understand. Here d is the duty cycle, which is less than 1, obviously. Okay. Beta is a greater than d. Beta is a greater than d. Okay. So what we have indicated here, from dt to beta t, inductor is releasing the energy, and from beta t to t, it is like a circuit is at a rest position. Are you getting the point? So 0 to dt, switch is in a on state, inductor is storing the energy, right? And dt to beta t, actually dt to capital T, switch is in a off state, but in that also dt to beta t only inductor is releasing the energy, right? And from beta t to capital T, it is like a circuit will be at the rest position. Means the inductor has released the energy till beta t only, right? So our inductor value is less than that of your L critical value, so that inductor is releasing the energy only till beta t. Okay, so from beta t to capital T, circuit will be at the rest position. So let me write here, t is equal to 0 to dt. 0 to dt, it is like a switch is on. Switch is on. Inductor stores energy. Inductor stores energy. Next, t is equal to dt to beta t. Switch is off. Inductor releases energy. Inductor releases energy. And t is equal to beta t to capital T. It is like a circuit will be at a rest position. Okay, circuit at rest position. Circuit at rest position. Right? Means inductor is not releasing the energy. Okay, because inductor has already released the energy, whatever it has. Right? So circuit will be at a rest position from beta t to t. Now for discontinuous conduction, we are going to derive the expression of V0 average. We are going to derive the expression for V0 average. Okay. Whatever the V0 average we have discussed, or we have derived V0 average is equal to D into Vs na, that was valid only for just continuous and your continuous conduction. That expression we cannot use for discontinuous conduction. Please be careful. For discontinuous conduction, now we are going to derive the expression. Are you getting the point? Right? So now here you can check from t is equal to 0 to dt. For t is equal to 0 to dt, it is like a switch is in a on state. Switch is in a on state. Okay. So if switch is in a on state, okay, means it is like a previous case only. So circuit will be like this. Whatever we already discussed. This is a switch here. Diode is an open circuit. Here it is a Vs, right? Inductor, which is storing the energy. Here it is a capacitor, and here it is a load, right? This is a load. V0, I0 is IC and C. Okay, this is inductor. Voltage across inductor is VL. This is Vs. So you can check here when switch is in a on state, that is during 0 to dt. Inductor is just storing the energy. Okay, so can I write VL is equal to what? It is a Vs minus V0. VL is equal to Vs minus V0, right? This is from 0 to dt only. For t is equal to dt to beta t. For t is equal to dt to beta t. Dt to beta t. Yes, switch is in a off state. Switch is in a off state. Inductor releases energy. Okay, inductor releases energy. Switch is off. Inductor is releasing the energy. Diode is in a conduction mode. And it is supply voltage, right? This is Vs, switch, diode D, inductor L. Voltage across inductor is VL, capacitor C, R. This is V0 and I0. Now, yes, can we write here VL is equal to minus V0? You can apply KVL, minus VL minus V0 is equal to 0. Okay, so therefore VL is equal to what? Minus V0. VL is equal to minus V0. Now beta t to t circuit will be at the rest position na, because inductor is not having any energy to release now. Okay, so it is like an open circuit. Diode is open circuit, switch is open circuit. Okay, so therefore now can we write the Holt second balance equation? Same, Holt second balance equation. Holt second balance equation. Balance equation. Holt second balance equation, right? So it is like a VL during on state of the switch, okay, into T on, plus VL during off state, but in that also during which interval inductor is releasing the energy? Only from dt to beta t. So let me write it as only beta t minus dt is equal to 0. Please try to understand this thing. Previously for continuous conduction, it was like T off was there. Now we need to consider during dt to beta t switch is in off state, no problem. But the inductor is releasing the energy only from beta dt to beta t, right? And from beta t to capital T, inductor is not having the any energy na, and circuit diode is in off state, switch is also in off state, right? So that's why your VL will be like a 0 only during that case, right? So we need to consider only this interval beta t to dt to beta t, right? So let me write it as what is VL during on time of the switch? It is Vs minus V0. Vs minus V0 into T on means dt plus VL during off time of the switch minus V0 into beta minus d into T is equal to 0, right? So further I can write it as therefore Vs into dt minus V0 into dt minus V0 into beta minus d into T is equal to 0, right? So further I can write Vs into dt is equal to, can I shift this V0 to the right hand side? Yes, so it is a dt plus beta minus d, okay? Or let me write it as, yes, V0 dt minus V0 into, this will be plus na, plus V0 into beta t minus V0 into dt, right? So V0 dt cancel out. So therefore I can write it as a tt also will get cancel out. So Vs into d is equal to V0 into beta. So this indicates your V0 is equal to d upon beta into Vs, d upon beta into Vs, right? What it indicates? This V0 means your V0 average. This is your V0 average. Be careful. This expression is valid only for discontinuous conduction. Discontinuous conduction, right? So, or let me write, indicate it as a V0 CCM also. That is a, sorry, DCM, discontinuous conduction mode. Okay. So, I'm writing it as a V0 DCM. That is a discontinuous conduction mode. Okay. So please try to understand. For continuous conduction mode, we are having V0 average is D into Vs. For discontinuous conduction mode, we are having a V0 average is equal to D upon beta into Vs. Okay, so for continuous conduction mode, continuous conduction, V0 average, let me write as V0 CCM. CCM is continuous conduction mode, is equal to D into Vs. For discontinuous conduction, we can write V0 average is equal to V0 discontinuous conduction mode is equal to D upon beta, right, into Vs, D upon beta into Vs. Okay, so now if we compare these two expressions, which one will be greater? Come on, which one will be greater? Whether V0 continuous conduction mode will be greater or V0 discontinuous conduction mode will be greater? Yes, can anyone? Please check. Beta value is less than 1, na? Beta value is less than 1. DCM is greater, right? DCM is greater. Are you getting the point? Because you can check. This is like D into Vs. For example, suppose D is equal to 0.6. So V0 CCM is 0.6 into Vs. And V0 DCM is, it is 0.6 upon beta, na? Whether beta is equal to 1 or less than 1, beta is less than 1. So suppose beta is 0.8 or 0.9. So you can check 0.6 divided by 0.8 will be greater than your 0.6, na? Right? So that's why here V0 DCM will be greater than your V0 CCM. Okay. So V0 DCM is greater than V0 CCM, right? Discontinuous conduction mode output voltage is greater than continuous conduction mode output voltage. Okay. So yes. So first thing is, as long as the numericals are considered, okay, we need to check whether the conduction is continuous or discontinuous. Blindly, we cannot use the continuous conduction expression, right? So we need to check in some of the numericals. Okay. So this is about your buck converter. Okay. Buck converter detailed analysis. So please check. We are having a 14-step procedure, simple circuit diagram. You need to memorize it. Okay. After that, first thing is what we done. We have analyzed the circuit when switch is in a on state. We have calculated VL and IC. Second thing, other parameters also we have calculated. Okay, just like your ID, ISW, IS, etc. Okay. Second thing, when switch is in a off state, again we have calculated VL and IC, and remaining parameters also additional we have calculated. Right. Next, we have used the Volt second balance equation. It is a VL during on time into T on plus VL during off time into T off is equal to 0. From that, we got the expression for V0 average in terms of your supply voltage. Next, we have written the ampere second balance equation. IC during on time into T on plus IC during off time into T off is equal to 0. Okay. From that, we got the relation between, yes, your load current and inductor current. Load current and inductor current. As long as the buck converter is considered, average value of inductor current is equal to average value of the load current. Right. Next, we have written the expression for the IL average. Okay. Or delta IL first. Okay. Delta IL means after that actually we drawn the waveforms, right? And after that IL average, delta IL max, IL mean, that is I1 and I2. Okay. ID average, switch current average value, source current average value. Okay. Critical inductance, critical capacitance, D at which the ripple is maximum, etc. Okay. So these parameters we have calculated. At the end, if the conduction is discontinuous. Okay. That we have discussed. Now we are going to discuss the boost converter. Okay. We are going to discuss the boost converter. So same procedure we are going to follow. Yes, beta means, Manikumar, the beta means the instant till which your inductor is releasing the energy, right? For the continuous conduction, it is like inductor was releasing the energy till time capital T, na? But here inductor for discontinuous conduction mode, inductor releases the energy before time T. So that instant is your beta, and beta value is always less than 1. Beta value is always less than 1 in this case. Okay. Don't get confused with this beta and your rectifier beta. Okay. In rectifier, that beta means angle it was. Here we are having the beta means the fraction here. Okay. Right. So Yes, if sir, if given L is less than L critical, yes, if L is less than L critical, then your conduction is a discontinuous. Okay. Right. Okay. So next, now we are going to discuss the boost converter. Boost converter. Right. So let us put the heading boost converter. Boost converter. It is same as that of your step up chopper. Okay, same as that of your step up chopper. You can check at this for the step up chopper. We connected the inductor at the supply side, na? Yes or no? Right? Next. So here boost converter, same circuit diagram. The only thing is we have added a capacitor here that is connected across the load. Boost converter. Vs, inductor, switch, diode, capacitor, resistor. Okay. So voltage across load is V0. Current flowing through the load is I0. Consider this current is IC. Voltage across capacitor is a VC. Diode current is a ID. This switch current is a ISW. IL. Voltage across inductor is a VL. And this is your IS. Okay, this is your IS, right? So we're having the boost converter, right? Boost converter. Now, yes, Karipe will discuss at the end of the session. Okay. Okay. Right. So now here again the same operation, same procedure we're going to follow. You can check inductor we have connected at the supply side. You can recall the step up chopper circuitry, and here in the boost converter also, right? We're having the inductor connected at the supply side, because boost converter means it is like your step up chopper only. Output voltage will be greater than that of the input voltage. Okay, and in order to get the output voltage greater than that of the input voltage, inductor is required to be connected at the source side. Okay, when switch is in off state, inductor voltage and supply voltage both will be getting added, and this full voltage will appear across the load actually, right? So that's why your output voltage will become greater than the supply voltage, right? So otherwise, if you remove inductor here, right? If we remove the inductor from the supply side, you will not get the output voltage greater than this supply voltage, right? So keep it in mind. This is the circuitry for boost converter. So next, let us follow the steps. So for t is equal to 0 to t on, that is dt. Okay, switch is in a on state. For t is equal to t on to capital T, switch is in a off state, right? Switch is in a off state. So switch is in a off state. Okay, so now let us first discuss circuit operation for t is equal to 0 to t on. So for t is equal to 0 to t on, switch is on. Okay, switch is on. So it is like a short circuit here. Okay, so this is connected. Next, what will happen? Current will flow like this, right? Current will not flow here. Current will flow like this. Okay, but this is the one thing, and at the same time, in the continuous conduction, it is like a capacitor will be discharging, because the thing is, if the switch is in a on state, okay, in order to get the constant current in the load for all time, right, we require, so during 0 to t1, capacitor is required to be discharged. Capacitor is discharging. Okay, so let us discuss the circuit operation. Also, from the waveform of IC, you will understand when the capacitor discharges and when the capacitor charges. Okay, so next, so for t is equal to 0 to t1, let me draw the same circuit again. Inductor, switch is on, supply voltage Vs. Here it is diode, which is in an off state. Capacitor C. Here it is a load, right? R, C, L Vs. Okay, so let me show this IL VL ISW ID IC VC V0, and this current is the I0, right? I0. Assumption, same assumption. V0 and I0, we are going to assume the constant. V0 and I0, we are going to assume the constant, right? Now, here, this is your diode D, right? Switch SW. So you can check when switch is in an on state, inductor stores energy. Inductor L stores energy. Next, so when inductor L stores energy, can we apply KVL to this loop? Yes, it is a plus Vs minus VL is equal to 0. Plus Vs minus VL is equal to 0. So can I write VL is equal to Vs? VL is equal to Vs. Yes or no? Right? Voltage across inductor is equal to source voltage. Next, can I write here VC? Definitely, capacitor is connected in parallel with the load. So VC is equal to V0, right? Next, diode current is 0 here. So you can check, consider this as a node X. If I apply KCL at node X, KCL at node X. So can I write ID is equal to IC plus I0? ID is 0, right? Because it is open circuit diode. So 0 is equal to IC plus I0. But I0 is our constant current, right? So I can write it as a capital I0. So therefore, IC is equal to minus I0. IC is equal to minus I0. IC is negative, the meaning is capacitor discharging. Capacitor is a discharging. Okay. So we're having VL, we're having the IC. Next, further can I write ID is 0. Additional things, ID is equal to 0 ampere. Next, can we write IL, IS and ISW all are same, right? Because we're having only one loop here. Okay. So IL, IS is equal to ISW is same as that of the IL. Inductor is storing the energy. So therefore, how will the nature of the current flowing through the inductor? Definitely it should be increasing. Na? Slope should be positive. Current flowing through the inductor will increase from I1 to the I2. Will increase from I1 to the I2, right? Next, here, yes, ID we have written, ISW we have written, right? So now this is for T is equal to 0 to T on. From T on to capital T, what will happen? For T is equal to T on to capital T. Let me write for T is equal to T on to capital T. T on to capital T. It is like a switch is open now. Switch is open. So you can check this circuit. If the switch is open, what will happen? Our inductor will oppose the change in the current. So inductor starts releasing the energy. Okay. So current will be, you can check. Now diode will be in a conduction mode. In this loop, the current will be flowing. It is like capacitor will be going charging. Capacitor go on charging. Okay. So we'll discuss for T is equal to T on to T. Right, let me draw the circuit first. Vs, inductor, switch is open, diode short circuit, capacitor, and here it is a resistor load, right? Load is a resistor. So this is Vs, L, switch, diode D, capacitor C and resistor. This voltage is V0, current is I0, this is IC, VC, diode current is ID, ISW, that is the switch current, inductor current IL, and this is the IS, right? Here it is a VL value. So now here inductor releases the energy, right? Let me write inductor L releases energy. Releases energy. So now can we apply KVL to the outer loop? KVL to the outer loop. It is like plus Vs minus VL minus V0 is equal to 0. Okay. So KVL to outer loop. KVL to outer loop. So it is a plus Vs minus VL minus V0 is equal to 0. No? You can check plus Vs minus VL minus V0 is equal to 0. Right. So therefore VL is equal to Vs minus V0. VL is equal to Vs minus V0. Right. Next, can we apply KCL at this node? KCL at node X. I can write ID is equal to IC plus I0. right? KCL at node X, ID is equal to IC plus I0. But ID is equal to IL, na? You can check current is flowing like this. So ID and IL both are same. Okay. So let me write IL is equal to IC plus, and I0 means current is constant. Okay. So I0. So therefore I can write IC is equal to IL minus I0. IC is equal to IL minus I0, right? So this is the current flowing through the capacitor. Okay. Capacitor current. It is IL minus I0, right? Next, can I write IS? This is IS. Okay. IS, IL, ID all are same. Yes. So let me write IS is equal to IL is equal to ID. All these are same. Okay. Next, you can check ISW. ISW is a 0. ISW is 0. ISW is a 0 ampere, right? So this is when T is equal to 0 to T on to capital T. That is when switch is in an off state. Next, now next step is hold second balance equation we need to write. Okay, so let me write hold second balance equation. So hold second balance equation. Hold second balance equation. Yes. So what is the hold second balance equation? VL during on time into T on plus VL during off time into T off is equal to 0. What is the voltage across inductor during on time? You can take it is a Vs, na? So Vs into T on. Let me write it as a Vs into T on means dt plus voltage across inductor during off time. Voltage across inductor during T on to T means off time. So it is equal to Vs minus V0. Okay. So it is a Vs minus V0 into T off. T off means T minus T on. T minus T on is equal to 0. So further we can write it as therefore Vs into dt plus Vs minus V0 into T minus dt, na? T on means dt is equal to 0. So this can be written as Vs into dt, right? Plus Vs into, I am writing it as 1 minus d into d, because T minus dt means 1 minus d into capital T. Okay. So minus V0 into 1 minus d into T is equal to 0, right? So therefore we can write it as this is Vs dt, and here it is, if I multiply this with Vs inside the bracket, that will be minus Vs into dt. So this will get cancelled. So it is like Vs into T is equal to V0 into 1 minus d into T, right? We check once. Something Vs minus V0 into T minus T1, right? Okay. So therefore minus V0 into 1 minus T into T, right? So Vs into T is equal to V0 into 1 minus D into T, right? So T will get cancelled. Yes. So therefore V0 I can write it as a 1 upon 1 minus D into Vs. Vs is a constant term, na? Vs is a constant. So can I say that here V0 means what? This is a V0 average only. Okay. So this is your V0 average. Whether it is the same as that of your step up chopper. Yes, in a step up chopper also we got this expression, na? You can check if D is less than 1. So therefore your output voltage is always greater than the supply voltage. So that's why it is a boost converter, or it is a step up chopper, like. Okay. So same expression we are getting, even though we have added a capacitor across the load, but your output voltage expression is not changing at all. Okay. But the only thing is we are getting the improved V0 and the improved I0 here, right? Next. So this is your hold second balance equation, and from that we got the V0 average. Next, can we write the ampere second balance equation? Yes, ampere second balance equation. Ampere second balance equation. IC during on time into T on plus IC during off time into T off is equal to 0. So we can write it as IC during on time. Please check the circuit. During on time, what is the IC? During on time, IC is equal to minus I0. Okay. So let me write it as a minus I0 into dt plus IC during off time. It is a IL minus I0, right? IL minus I0. So IL minus I0 into T off means it is like a T on plus T minus T on, right? T minus T on is equal to 0. So we can write it as therefore minus I0 into dt plus IL minus I0 into 1 minus D into T is equal to 0, right? T minus T on is 1 minus D into T, right? So now we can write it as therefore you can check minus I0 dt, or let me write minus I0 into dt plus IL into 1 minus D into T minus I0 into 1 minus D into T is equal to 0. This is minus I0 dt, and here it is minus, and this minus it will become plus I0 dt will get cancelled out. So I can write IL into 1 minus D into T is equal to I0 into T, na? Right? So T will get cancelled out. So therefore I can write IL is equal to 1 upon 1 minus D into I0. Be careful. This is the expression for inductor current. Inductor current is equal to 1 upon 1 minus D into I0. So what it indicates, as I0 is a constant, so can I say that this expression of IL is nothing but your IL average only. IL average only. So please try to understand here. D is always less than 1. So can I say that here average inductor current is greater than load current? Yes or no? Yes, D is always less than 1. So therefore, average value of inductor current is greater than the load current, right? So it is not like I0 is equal to 1 upon 1 minus D into IL. No, it is IL is equal to 1 upon 1 minus D into I0. Okay. So therefore, inductor current is average value of inductor current is greater than the load current. Let me write average inductor as D is less than 1. So therefore, IL average is greater than I0. IL average is greater than I0, right? Next. So now we're having the expression for IL average. We're having the expression for inductor voltage as well as load voltage. Okay. Now can we draw the waveforms? Yes. So let me draw first. IL waveform, let us draw. Time t 0 to T on to T, and T on T to T plus T on. So you can check here. Yes. First thing is 0 to T on, inductor is storing the energy. So definitely inductor current will increase from I1 to I2. Right? This is a I1, this is a I2. Next, during T on to T, switch is off, inductor releases the energy. So again current will fall down to I1. Okay. This is a linear only, and again increases to the I2 value, and it go on repeating, right? So your inductor current is varying between I1 and I2, right? Next. So what is the delta IL? Can I indicate delta IL means difference between the two? This is your delta IL. Okay. So let me write here. This is the delta IL. What is the IL average? This is a linearly increasing, linearly decreasing. So IL average is equal to your center point passing through the center point now. So it is I1 plus I2 by 2. Okay, I1 plus I2 by 2. So let me draw IL average waveform. Okay, so it is I1 plus I2 by 2. Or let me draw on the next plot. No, better put it. So IL average will be like this. This is your IL average. Okay. IL average, right? Which is equal to I1 plus I2 by 2 actually. Okay. Next, delta IL is this full I2 minus I1 is the delta IL. Be careful, right? So this is your delta IL. Next, now IL waveform we are having. Can we draw the waveform of I0? Yes, I can draw I0 waveform. I0 waveform is a constant waveform, no? It is a constant current, but you can check I0 is less than IL average. I0 is less than IL average. We have written this is your I0 magnitude. How is the waveform of IC? Waveform of IC. T1 to T, T to T plus T1. Yes, IC waveform. You can check during T is equal to 0 to T1. Switch is on state, diode is in a off state. IC is minus I0. Na? We have written. When switch is in a on state, IC is equal to minus I0. We have written. Yes, minus I0. Okay. So minus I0 means I0 is your positive. So IC will be negative. Minus I0. This is your IC. It is a minus I0. Right? 0 to T1. 0 to T1. When switch is in a on state. When switch is in a on state. Yes. What is the IC? When switch is in a on state, IC is IL minus I0. Okay. IL minus I0. So you can check here. When switch is in a on state, if we want to draw, this is I2 na? At this instant, IL is I2. I2 minus this I0. So it will be positive only. It will be positive only, right? After that, as IL decreases, your IL minus I0 difference go on decreasing. So it will be like this. This will continue like this. And after that, after one complete cycle, again it repeats. Just try to understand. So this indicates your IL minus I0. IL minus I0. This is like I2 minus I0. This point is like I2 minus I0. And this point is like I1 minus I0.
Sir,
Because
repeat this IC waveform again.
Okay, okay, I will. Okay, so please check when switch is in a on state. Yes, T plus T1. When switch is in a on state, what is IC? IC is minus I0, na? So 0 to T1, IC is a constant, that is a minus I0 only. At T1, that is T1 to T, IC is a IL minus I0. At T1, you can check at T is equal to T1, IL is I2, na? Right? So I2 minus this value is nothing but your I2 minus I0. After that, your IL decreases. After that, your IL decreases. So IL minus I0 will be like this. Don't get confused. In this boost converter, IL average and I0 both are not same. Are you getting the point? In the buck converter, these two were same, IL average and I0. But in this case, you can check. We're having IL average is 1 upon 1 minus D into I0. Na? So your IL average is greater than that of your I0. Right? Greater than that of I0. So that's why the difference, if you take this waveform and this waveform, the difference will be like this only. Okay. So because I0 is constant only, na? I0 is a constant. So this is your IC waveform. IC waveform. Now we know the IC waveform. So can we draw the VC waveform? Yes, VC waveform. How is the VC waveform? When current is negative, it is like capacitor charges or discharges. When IC is negative, capacitor will be charging or discharging. IC negative means it is like a capacitor current direction is in upward direction. Na? So it will be like a discharging. Are you getting the point? Capacitor will be discharging. So when IC is negative, capacitor will be discharging. During 0 to T1, capacitor discharges. T1 to T IC positive, capacitor will be charging. Capacitor will be charging. So let me write here. Yes, capacitor will be discharging and charging like this. So capacitor waveform will be like this. Discharges and again charges, right? So and after that again discharges, right? And again charges. It will be like this. Okay. So it will vary between peak capacitor voltage and or maximum and the minimum value of the capacitor voltage. Okay. So this indicates this point minus this point now. So it indicates your delta VC. This indicates the delta VC. Let me show here. This is the delta VC, right? Delta VC, which is equal to delta V0 again, which is equal to delta V0, right? Next, now can we draw the waveform of switch current ISW? Switch current ISW. Yes. During 0 to T on, what is the switch current? Come on, speak out. During 0 to T1, that is when switch is in a on state. When switch is in a on state, can I say that IL and ISW both are same? Yes or no? Right? Yes. Yes, I will tell you how to find the VC expression, right? Okay. So during 0 to T1, when switch is in a on state, okay, ISW is same as that of your inductor current now. We have written when switch is in a on state, you can check here. Yes, IS, ISW and IL both are same now. When switch is in a on state here, IS, ISW, IL all are same. Okay, so therefore let me write it as it is a same as that of the inductor current, means what? It is changing from I1 to I2. This is I1, this is I2. Same as that of the inductor current, IL. After that, when switch is in an off state, switch current will be definitely 0 now. So that's why it is a 0. And same again repeats. This will repeat, right? Same. So this is your switch current waveform. Can we draw the IS waveform now? IS waveform. Yes, how it will be? Yes, IS waveform and IL waveform. IS and IL waveform both will be same or different? IS and IL waveform both will be same or different? Come on. You can check the circuit operation. When switch is in on state, IS and IL both are same. When switch is in off state, again the same, right? So IS and IL waveform will be same. So it is like this: I1 to I2, I2 to I1, I1 to I2, and again this is this. So this is like your I1, this is like your I2, same as that of the inductor current, right? Same as that of the inductor current, right? So inductor current average value expression can be used for IS average also, right? So this is the IS waveform. We can draw the ID waveform also. How is the ID waveform? ID waveform 0 to T on to T, T to T plus T on. Yes. When switch is in on state, diode is in off state. Okay, so ID will be 0. When switch is in off state, inductor releases the energy through the diode, na? So ID and IL both will be same. Okay, so ID waveform will be like this, right? So we'll be having this type of waveform. Same as that of the inductor, but during only this period. Again 0 and again same repeats. It is changing from I2 to I1. This is the I2, this is the I1, and this is same as that of the IL, right? Next, so these are about the waveforms. Now let us find the delta IL. Let us find the delta IL. That is ripple in inductor current. Let me write ripple in inductor current. Ripple in inductor current, right? So delta IL. How to find? So same as that of your buck converter procedure. Either you can apply KVL to the loop during on time of the switch or during the off time of the switch. Okay, in both the ways you will be getting the same wave expression. Okay, so let me write during, yes, for T is equal to 0 to T on. We're having the circuit, switch is in a on state, na? Okay, so instead of drawing circuit, I am directly writing expression. VL is equal to VS. We are having. Please check. When switch is in a on state, current was flowing like supply voltage, inductor, switch, and again back to this loop only, na? Diode was in off state, capacitor was discharging. Okay, So VL is equal to VS only we are having. So VL means what? L into DIL by dt is equal to VS, right? Now what is the DIL? Change in the inductor current. During 0 to t on, how the inductor current is changing? Inductor current is changing from I1 to I2. Okay. So let me write it as L into I2 minus I1 divided by dt means t on minus 0 is equal to Vs. Okay. So further can we write it as therefore L into I2 minus I1 means your delta IL, peak to peak ripple current. Okay. Inductor. So delta IL divided by t on is equal to Vs. So we can write it as therefore delta IL is equal to Vs into t on means dt divided by L. Okay, Vs into dt divided by L. This is your expression for delta IL, right? Ripple in inductor current, that is I2 minus I1. Okay, let me write it as which is equal to I2 minus I1 actually. Okay, so next, can I write IL average expression? Yes, average value of inductor current, average inductor current, average inductor current. We have already written. In other way also, we can write IL average is equal to I1 plus I2 by 2. Na? Again, it is equal to 1 upon 1 minus d into I0. We have written this expression from ampere second balance equation. Okay, 1 upon 1 minus d into I0. IL average is I1 plus I2 by 2, which is equal to 1 upon 1 minus d into I0. Right? Next, can I write IL max? IL max, maximum inductor current. Maximum inductor current. That is IL max, which is equal to, in our case, it is I2 now. We have represented with I2. So can I write IL max is equal to I2, which is equal to IL average plus delta IL by 2 now. You can check the IL waveform, you will understand. Yes, this is the IL waveform. IL average means this green curve, green line. Okay. So IL average plus this full is delta IL. So IL average plus delta IL by 2 means I2. Okay. So IL average plus delta IL by 2. So further I can write it as 1 upon 1 minus d into I0 plus delta IL by 2. Okay. Next, minimum inductor current. Inductor current. IL min, which is equal to I1. Na? In our case, it is I1 we considered. So therefore, IL min, which is equal to I1, which is equal to IL average minus delta IL divided by 2, right? Minus delta IL divided by 2, right? So we have written the whole second balance, ripple in inductor current, IL max, IL min, right? Next, can we find the IS average source current average value? Average source current. Average source current. IS average. Whether it will be same as that of the IL average or not. We know IS average and IL. IS and IL both are same, na? So therefore, IS average is equal to IL average, right? Which is equal to 1 upon 1 minus d into I0, right? This is your average value of source current. Next, average value of switch current. Average switch current. Average switch current. Average switch current. Okay, so ISW average we need to write. So for that, you can check the switch current waveform. How it is 0 to t on, it is same as that of the IL, na? T on to t, it is a 0. Okay, so let me draw first ISW waveform once again here. So ISW, this is a time t 0 to t on to t and t to t plus t on. It is like this, I1 to I2, that is same as that of the inductor current, and during this interval again it is 0, right? Same repeats. So this is I1 Here it is a I2. So can I approximate this waveform? Yes, as ISW time t. I am approximating this as an average. This is a T on, this is a T, right? What is the average here? I1 plus I2 by 2 means again IL average. So same here, 0. You can check, this indicates your IL average. Next, so can I write ISW average? So therefore, ISW average is equal to 1 by T integration from 0 to T on. Yes, IL average into dt. So this can be written as duty cycle D into IL average. Or further we can write D upon 1 minus D na, into I0. This is the switch current average value. Right? So ISW average. So this is the average value of switch current. Right? Next, can we find the average value of diode current also? ID average. Average diode current. ID average. How is the ID waveform? Yes. When switch is in on state, diode is in off state. So current is 0. When switch is in a off state, diode is in a conduction mode. Inductor releases the energy. Na? IL and ID both are same. So it is like this. So we're having this type of waveform, right? This is I2. This is I1, same as that of your IL. So further, I can approximate this as this is a T on, T plus T on, right? I1 plus I2 by 2, that is the IL average only. 0, 0. Again, same repeats. This should be a straight line. Same magnitude. This is your IL average. So what is ID average? Can I write ID average is equal to 1 by T integration from T on to T. IL average into dt na, so which is equal to, if you simplify, you will be getting it as 1 minus duty cycle into IL average. This is your ID average, right? Average value of diode current, correct? Next, now the next point is ripple in capacitor voltage. Yes, ripple in capacitor voltage. In the previous case, that is for the buck converter, how we have calculated ripple in capacitor voltage? Yes, it is a delta VC is equal to delta Q by C, we wrote na, right? So same here, can I write delta VC is equal to delta Q upon C only? Okay, so this is your delta VC, which is equal to again delta V0, because capacitor is connected across the load. Now we need to find the delta Q. We need to find the delta Q. Delta VC means change in the capacitor voltage, which is equal to delta Q by C. So for that, we need to check the IC waveform and VC waveform. IC and VC waveform. So let us check IC and VC waveforms. Yes, here it is. Here it is IC waveform, and you can check we are having a VC waveform. What the delta VC indicates? Delta VC is nothing but the change in the capacitor voltage. So you can check during 0 to T on, capacitor voltage is changing from maximum value to the minimum value. So can I say that this is nothing but difference between these two voltages is nothing but the delta VC? So corresponding to 0 to T on, you can check what is the IC. IC is here. It is a constant current. So can I say that the area under this rectangle is nothing but your delta Q? Yes or no? Delta Q, right? So delta Q is equal to, we can write I0 into T on, I0 into T on. So let me write it as I0 into T on, which is equal to I0 into T on divided by C. This is your delta Vc. Further, we can write it as, which is equal to I0 into T on means dt divided by C, delta Vc. Further, this can be written, therefore delta Vc is equal to I0 into D divided by F into C. T is nothing but 1 by F na? So it is a F into C. This is your delta Vc. So from this you can check. In order to minimize the delta Vc, means what? In order to get the nearly constant capacitor voltage na, right? Means we are minimizing the maximum value of the capacitor voltage and minimum value of the capacitor voltage, means this difference we are minimizing. You can check this waveform. Yes, here it is. We are minimizing this difference. This difference we are minimizing means nearly we are trying to get the constant capacitor voltage. So here, in order to get the constant capacitor voltage, that is to minimize the delta Vc, what is required? Your capacitor value should be more and the switching frequency should be more. Okay, so let me write. Yes, delta Vc can be minimized by increasing capacitor C, increasing C and frequency F, switching frequency F. Yes, capacitor increases means definitely your opposition to the change in voltage increases. So you'll be getting nearly constant voltage. Okay, means there will not be change. Next, switching frequency increases means your time t decreases. Time t decreases means your T on decreases. Obviously, your T off is also decreases. Okay, so that's this is delta Vc can be minimized by increasing C and F. Right. Next, yeah. Now you can check here. Delta Vc is proportional to the D na. Delta Vc is proportional to the D. So let me write here. Yes. Delta Vc is equal to I0 into D by Fc. I0 into D by F into C. Okay. So as delta Vc is proportional to duty cycle D. So can I say that more the duty cycle, more will be the delta Vc? Yes. So as duty cycle D increases, delta Vc increases. Delta Vc increases, right? So therefore, at the maximum possible duty cycle, therefore at maximum D, okay, which is equal to D max, delta Vc will be maximum. Delta Vc will be maximum. And what will the value of that maximum duty cycle? That depends on your circuit parameters. Okay. In I think one of the example they have asked this one. Okay, we'll discuss at that time. So at Dmax, the delta Vc will be maximum. Similarly, you can check a delta IL expression. We're having a delta IL expression also. In that you can check the duty cycle at which the delta IL is maximum, na? Right? So here delta IL is Vs into dt by L. Delta IL is Vs into dt by L. Let me write here. Delta IL is equal to Vs into dt divided by L. Okay. So can I say that delta IL is proportional to duty cycle D. So therefore, more the duty cycle, more will be delta IL. Delta IL. So therefore, at D is equal to D max, delta IL will be maximum. You can check, and definitely this Dmax will be less than 1. Dmax will be less than 1, right? For example, suppose in a boost converter, recall the boost converter circuit. Okay, where having the supply voltage, inductor, switch, diode, capacitor, and a load. Suppose in the boost converter, if I keep the D is equal to 1, what will happen? What will the output voltage? In one of the examination, they asked the question. In a boost converter, if D is equal to 1, duty cycle is equal to 1, what will be the V0? Come on, or V0 average? Can anyone? Some are saying infinite, some are saying 0. Okay. Don't go blindly for that V0 average is equal to 1 upon 1 minus D into Vs. No, you can check the circuit. Yes. Yes, this circuit. If I am keeping D is equal to 1, D is equal to 1, the meaning is we know D is equal to T on by T. Na? So if D is equal to 1 means your T on is equal to total time T. Yes or no? Right? So if D is equal to 1 means T on by T is equal to 1. The meaning is your T on is equal to total time. So here, if T on time is equal to total time, so can we say that here off time will be absent? So the meaning is switch will be in a on state for all the time. Switch will be in a on state for all the time. So if switch is in a on state for off the time, it is like current will be flowing into this loop only. What about the load current? Initially it is turned on, so current starts flowing here. Capacitor will be suppose discharging. Okay, capacitor will be discharging. Okay, now but it will be discharging only for some certain period. Na? After that, what will happen? Whether the off time is present in the switch? No. In the circuit, as D is equal to 1, off time will be 0. Off time is 0, so it is like switch is in a on state only for all time. So capacitor will not be getting time to charge, na? And inductor is not releasing the energy because off time is absent here. So that's why your load voltage will become 0. It is not like that. We are having V0 average is equal to 1 upon 1 minus D into Vs. So simply if I am putting D is equal to 1, it is like 1 upon 1 minus 1. So 1 upon 1 minus 1 means 1 upon 0. So it is infinity. So output voltage is infinite. No, they will be giving 100%. They will give the one option as infinite. But we cannot blindly use that expression. Think about the circuit operation. Right? So in the circuit operation, if D is equal to 1, T on is equal to capital T. So off time will be 0. Off time is 0 means this switch will be in on state only. Inductor will not be getting the time to charge. Okay. So that's why, yes, capacitor will not be getting time to charge as the off time is 0. Right. So capacitor is not charging. That's why your output voltage will be 0 only. Right. So, yes. Yes. So this is about D is equal to D max, delta IL will be maximum. Okay. Next point is critical inductance and critical capacitance, right? Critical inductance and critical capacitance. So let me write critical inductance. Please don't raise the hand. At the end of session, we will discuss. Okay. Sunil Wagmare. Critical inductance, that is L critical. So corresponding to the critical inductance, yes, we know IL waveform will be like this. We have discussed in the boost converter also. T on to T and T to T plus T on. So current will be increasing from 0, next decreases to this value and again increases, right? This type of waveform will be getting. So this is like your peak value, that is the I2. I1 is like a 0 na. So can I write delta IL means this only. So IL average is delta IL by 2. Okay, so IL average is equal to what? Delta IL by 2 only. Okay, delta IL by 2. Now what is IL average? IL average is 1 upon 1 minus D into I0. 1 upon 1 minus D into I0 is equal to delta IL by 2. What is the delta IL we have written here? Delta IL, yes, Vs into dt by L. Okay, so it is Vs into dt divided by L. So it is a 2L, right? So from this, I can write it as, therefore, further we can write this I0 with, I can replace with a V0 by R. Okay, so it is like a V0 by R divided by 1 minus D is equal to Vs into dt divided by 2 into L, right? So further this can be written as, therefore, I can write here, I can replace D in terms of Vs, okay, as 1 upon 1 minus D, okay, into Vs. So this can be written as 1 upon 1 minus D bracket square into R na here, right? Into Vs, which is equal to Vs into D into T divided by 2 into L. So Vs will get cancelled out, right? So further we can write L critical from this expression. Therefore, L critical is equal to, you can check L critical dt upon D into 1 minus D square into RT divided by 2, right? Divided by 2. Or this can be written as D into 1 minus D bracket square into R divided by 2F. This is a critical value of inductor. Either you can use in terms of frequency or you can use in terms of the total time T, right? Next. So this is L critical. What about R critical? R critical. Simply replace L critical with L, that is the normal value of inductor, and here put R is equal to R critical. So it is equal to 2FL divided by D into 1 minus D bracket square. Okay. This is your R critical. Next, can we find the critical value of capacitor? Yes. Critical capacitor. Critical capacitor. C critical. Yes, we know, just like this thing, whatever we written here, IL average is equal to delta IL by 2. So here we can write V0 average or VC average, which is equal to V0 average is equal to delta VC by 2 na. So V0 average is equal to, or let me write V0 is equal to, what is delta VC? We have written here delta VC. I0 into D by FC. I0 into D upon F into C, and these two as it is. Okay. So therefore I can write it as, further we can write this, we can replace this I0 with a V0 by R. So V0 is equal to V0 by R into D here, that is 2R F into C. V0 will get cancelled out. So therefore I can write C critical is equal to D upon 2FR, right? D upon 2FR, or which can be written as dt by 2R, right? This is a C critical. Yes or no, right? So this is C critical. Now, next point, if the conduction is discontinuous, then what to do? Yes, if conduction is a discontinuous, conduction is discontinuous. Okay. So conduction is discontinuous means it is like your IL waveform will be like this. This should be T na, and it is somewhat T plus T1. So for discontinuous conduction, it is increasing from 0 to maximum value, it decreases and reaches to 0. And again, same repeats. Okay. So dt on is nothing but your dt. And suppose this is a beta t, right? So this is your I2, that is the maximum value. Now what is happening during 0 to t on? Inductor is storing the energy. T on to beta t, inductor releases energy. Beta t to t, circuit will be at the rest position. Okay. So I'm writing Holt second balance equation. So Holt second balance equation, we can write. So it is like VL during on time of the switch into T on plus voltage across inductor during off time of the switch into beta t minus dt is equal to 0, right? Next, so VL during on time of the switch is Vs. You can recall the circuit, switch is in on state, VL is equal to Vs, okay? Vs into dt plus, what is the VL during off time of the switch? During off time of the switch, you can check VL is equal to, it is like plus Vs minus VL minus V0 is equal to 0. So VL is equal to like your Vs minus V0, okay? So yes or no? Beta minus d into t is equal to 0, right? So you can check now, plus Vs minus VL minus V0 is equal to 0. So VL is Vs minus V0, right? So further we can write it as, so therefore Vs dt plus Vs into beta minus d into t minus V0 into beta minus d into t is equal to 0, right? So plus Vs dt minus Vs dt will get cancelled out. So it will be like only Vs beta t will remain here, which is equal to V0 into beta minus d into t. Tt will get cancelled out. So therefore V0 is equal to beta upon beta minus d into Vs. This is your V0 average. This is for discontinuous conduction mode. Discontinuous conduction mode. So let me write here V0 average for continuous conduction. Continuous conduction. We are having V0. Let me write it as a continuous conduction mode. Okay, is equal to where we wrote 1 upon 1 minus d into Vs na. Similarly, V0 average for discontinuous conduction mode. V0 DCM, discontinuous conduction mode, is equal to just now derived beta upon beta minus d. Beta upon beta minus d into Vs. So if you compare these two, which value will be greater? You can check here, it is a 1 minus d, here it is a beta minus d, right? Obviously here it is numerator 1, it is a beta we are having, okay? But if you compare, you can check any value. You can select d is equal to, for example, suppose 0.6, beta is equal to 0.8, 0.9, and you can compare, okay? We'll be getting, because this difference, this value beta minus d is comparatively very less, right, than that of your difference between 1 and beta, okay? So V0 DCM is greater than V0 CCM, right? Discontinuous conduction mode V0 is greater than continuous conduction mode V0, right? So yeah, shall we discuss the numericals? Yes, no? No, everybody is saying no, huh? How to complete the syllabus till Friday, huh? Okay, we'll take a doubt clearing session, right? Tomorrow we'll discuss the numericals related to the buck converter, boost converter, okay? And after that we'll be discussing about the buck boost converter, right? So as long as this chapter is considered numericals are definitely we are going to solve tomorrow at the start. After that the buck boost converter, right? After that the effect of inductor resistance. After that the effect of inductor resistance we are going to discuss. And next, if you recall in the chapter number 1, that is the switching devices, we already covered the voltage commutation and voltage commutation circuit and current commutation circuit, okay? And from this chapter, we have already solved the 2 numericals. Remaining numericals we are going to solve tomorrow, okay? So probably tomorrow we'll finish this chapter, right? Okay. Yes, Ramakrishna, sir, you didn't discuss principle of operation of step down up chopper. Not required, because your basic chopper circuit and this regulator circuit, both are giving the same operation, na? Same output voltage expression. Okay. So not recorded, because only the thing is we discussed the step up and step down, right? In order to understand what is the expression of that V0 average and V0 RMS, right? And what is the drawback of the basic chopper circuit, right? So for that we discuss that step up, step down. Tomorrow we'll discuss direct buck boost converter. Buck boost converter is like your step up, step down chopper only, right? Okay.
Sir,
Yes, please.
sir, that capacitive waveform, the VC,
Capacitive
capacitor waveform VC, in the case
VC.
of buck and boost.
buck boost.
No, buck separate, boost separate.
Okay, okay, huh?
There, that waveform is exponential, or is it that the rise is exponential, sir? This thing.
Okay, this VC waveform you are saying.
Yes, sir.
No, it depends on the nature of your current flowing through the capacitor. Because in the capacitor we know na VC is equal to 1 by C integration of IC dt. As this IC is a constant here.
Yes, sir.
So that's why it is a linear here.
Oh, so it's linear only.
Yeah, linear only. Right?
Yeah, same in the case of buck also.
Same in the buck also we're having it is a in the buck you can say it is like a parabolic.
Okay, sir.
Because the thing is in the buck we're having IC is equal to IL minus I0 na.
Oh, yes, sir.
I0 is constant we're having.
Yes.
IL is changing linearly.
Yes.
So if you take the difference IL minus I0, that will be also changing linearly. That is
Integration
minus
will
delta
give
IL plus delta IL by, right?
So
So what is the integration of that linear thing? It is like a parabolic.
parabolic.
Right?
Yes, sir.
Yes.
Okay, sir.
Okay.
So this notes, can we get it by today, sir?
Yeah. All daily what I am doing after the session, immediately I am uploading the notes, right?
Okay, sir. Okay, sir.
Right.
Thank you, sir.
Okay. Yes. Yeah, if you are having any doubts, please ask.
Hello, good evening, sir.
Good evening.
Sir, that for L critical value.
All points, sir.
Just a minute,
for
one by one. I think
for that some L value, I am getting some discontinuous conduction.
Where please repeat.
Then for we will get some beta. Then IL in buck converter, that is IL is equals to IC plus
No,
I0.
please repeat everything whatever you are saying.
There in a buck converter.
In a buck converter.
Audio. IL is equals to IC plus I naught for t barabar 0 to t barabar t on.
IL is equal to IC plus I0.
Okay. For some value of can I say that for any value of for that critical value of capacitor and that critical value of inductor, that will be to find L critical we have to substitute C critical value.
To find the L critical.
Can I put C critical?
No, it is not like that. Please listen. Two things we are having. One is a L critical and second one is a C critical. If your L is equal to L critical, then your IL waveform is whatever just now I told na, that is just continuous.
Yes.
And if C is equal to C critical, then your VC waveform is like your just continuous. Means what will happen? VC will be C just continuous, means this will be right. This point will be reaching to the 0 here. Means this waveform will be shifting to the in a downward direction. So it is not
Sir,
like that. In order to find the C critical, it is not required to put L is equal to L critical. Are you getting the point?
Yes, sir.
Right? Okay.
But I can write IL is equals to IC plus I naught.
So
for some value of if L is less than L critical, then it will be discontinuous conduction.
Yes.
then C will be means IC will be discontinuous.
If L,
Means
you are
IC
saying
will be,
L, if you are saying L is less than L critical, then IL will be discontinuous.
IL, okay, IL will be discontinuous. From that waveform we can we say that you draw the graph that for T/2 it is charging, another T/2 it is discharging.
In a buck converter.
Then that waveform will be definitely going to change.
Yeah, definitely it will change.
Then for calculate that value of C, how we can conclude?
C value
that
is
case-
required for a delta VC, na? Or VC
Delta V. Then IC waveform will be changed from that you have drawn, will be changed from that waveform. Then from that new waveform we have to calculate.
Yes. From that new waveform we need to calculate.
In some problems are actually numericals. I got that problem, but it is unable to. Means at some point I'm not getting how to solve it from next step. Means L value in form of capacitor, but can I put C critical for L critical? There is no point of that.
Okay. Whether that
Okay.
problem is there in our booklet?
I think sir in test series actually I get.
Okay, in a test series. So
Okay, I will send that
send me
question.
that question. I will check. Okay.
Yes sir.
Okay.
Sir, at 193 F, sir.
Yes.
At 193 F, sir.
193.
Yes, sir.
Yes.
Sir, why the inductor waveform is not starting from 0? Sir?
Why the inductor IL waveform?
Yes, sir.
Because it is for steady state operation we are discussing.
Sir, even if for steady state, like before turning on the switch, the current through the inductor should be 0, right, sir?
Before turning on the switch,
The current through the inductor it should be 0.
please listen. Whatever you are saying or whatever you are thinking, that is for very first cycle is true. Very first cycle it will start from 0.
Okay, sir.
But in a continuous cycle, what is happening? Suppose inductor for very first cycle inductor current is changing from 0 to, let us consider, 10 ampere.
Okay, sir.
And after that, during the I have maintained the off time such that the current flowing through the inductor is changing from 10 ampere to the 2 ampere only.
Okay.
I'm not letting the inductor to release the energy fully, because I am respecting the off time.
Yes, sir.
So now current
it's like we are
from this point to again this value, na?
Okay, sir.
So that's why it is continuous conduction. It is jumping between I1 and I2 only.
Okay, we are neglecting the transient period of the inductor.
Yeah, we are neglecting because simply transient period is for very short time, na?
Okay, sir.
Right? So we're neglecting it. Okay.
Sir, and then one more doubt. Like for continuous conduction, the inductance value should be high and the switching frequency should be low. Is it right, sir?
Yes, correct.
Sir, and then 227 F, sir. 227.
227. Yes.
Sir, for the voltage across the capacitor waveform, like from 0 to T1, why is it getting discharged?
Okay, because here capacitor current is negative, na?
Okay, sir, but the circuit from 0 to T1, the capacitor is in, like the capacitor don't have any supply.
You are thinking in for a very first cycle. For continuous cycle, you can check for continuous cycle.
Yes, sir, got it, sir.
We are having the two things. When capacitor charges, means current in a capacitor is a downward direction, it is a positive.
Yes, sir.
Capacitor discharges means current is in upward direction, that is a negative.
Direction.
Same thing, right?
Okay, sir. Got it, sir. Thank you, sir.
Yes,
sir, in the discontinuous mode, sir,
discontinuous
in
conduction. This
buck converter,
converter.
average voltage is greater, no, sir, in discontinuous mode.
Yes.
Will it be a good idea to operate this converter in discontinuous mode, sir?
Okay.
Current is also coming large as compared to continuous mode, no, sir?
Yes, current is also increasing, in some of the cases we are operating as a discontinuous conduction. But the thing is, you can check in a discontinuous conduction, your voltage is improving. Let me open it.
Yes, sir.
Yes. This is na.
Yes, sir.
So you can check here. Yes. What I am doing, inductor. I think I have not drawn the waveform of IL. Yes, here it is. Okay. You can check average value of inductor current in this case and average value of inductor current in a continuous conduction case. In which case it will be more?
In the continuous
In
mode, sir.
continuous conduction, inductor current value will be more. Okay.
Yes, sir.
Here inductor current value is less. Okay.
Yes, sir.
Even though we are getting the output voltage greater than your continuous conduction mode. Okay.
Okay.
Definitely, if load is resistive or any load, your I0 will be more. No problem. Okay.
Okay, sir.
Right. But the thing is, here IL is your having the value lesser than that of the whatever the IL average in a continuous conduction.
Yes, sir.
So for some of the cases, we can operate in a discontinuous conduction. Even in the numericals also they have given. But generally, they don't specify whether it is a continuous or discontinuous. From the value of supply voltage and output voltage and the duty cycle, we are supposed to find whether it is a continuous or discontinuous.
Okay, sir. Okay, sir.
Hello, sir.
Huh.
Sir, in boost converter, we will in
Yes,
the
yes,
capacitor
please.
current.
In a
Hello, sir. In the boost converter,
yes.
sir, we put in
Ah.
capacitor current. Could you explain that how you take the delta Q?
Okay. Delta
It's
Q,
from-
how I have calculated?
Hi, sir, from T on to T now, sir. That,
Yes, 0 to T on. Na?
no, T on to T will take now, sir, for the increment of the delta VC.
Delta VC, you want how to find? Na?
Hi, yes, sir.
Just a minute. Delta VC, delta Q by C, is it fine?
Hi, yes, sir.
Okay, now let me go to the yes VC waveform. Yes, this is a VC waveform we are having, right?
Hi, yes, sir.
So suppose if we want to find the delta Q from T1 to T, na?
Yes, sir.
This is what you are saying, na?
Yes, sir.
Okay, then I need to check area under this curve.
Yes, sir.
Okay, so for that I need to, yes, first of all, divide it like this. Area under the triangle and area under this rectangle I need to find. That
Yes,
will
sir.
give you the delta Q, right? Both the delta Q will be same.
Sir, the addition of the from square plus rectangular both are there. No, sir.
Yes, yes.
We are taking approximate or we'll take total area that one.
No, no,
In that,
both this area only. Either
Huh.
this area or this area we need to take. Because the thing is, what is the VC waveform? It is changing from Imax to Imin. VC max to VC min, and VC min to VC max. It is again changing. We are interested only in delta VC.
From T on to T.
The capacitor voltage is changing from maximum to the minimum only during 0 to T on, or you can say during T on to T.
Yes, sir. Yes, sir.
So in order to find the delta Q, either I need to take 0 to T on area or T1 to T area, right?
Yes, sir. I will. Thank you, sir.
Ah, yes. Yes, next.
Hello, good evening, sir.
Ah, good evening.
Sir, that boost equation, boost 1/1 minus d into Vs, V out is equal to. If anyone asks,
Please, will you please speak a bit louder?
yeah, sir. Sir, that boost converter equation,
Okay.
V out is equal to 1/1 minus d into Vs. Can we? If anyone asks that if equation valid at d is equal to 1, then we can say that it's invalid.
Yes, yes, yes. It is invalid.
It's invalid.
Because actually the thing is, for any converter, there is a limit for a maximum value of duty cycle.
Right, sir.
And that expression is valid only till Dmax. Huh?
Right.
And that Dmax is always less than 1.
Okay, sir.
Sir, sir, that one D equal to 1 only for the that case is invalid, no, sir? Or else
What?
just he asked no, sir, that question. For the D equal to 1,
Huh.
this only invalid for the D equal to 1. Other than that value, all this value.
No. It is actually invalid whatever
Only
we have
for-
discussed na circuit operation, it is valid only till D is equal to D max. That D max might be 0.9, 0.85, etc. Right?
Okay, sir.
After that, that cannot, that expression will not valid.
Okay, then buck converter.
Because the thing is, we will not be getting the steady state operation. The steady state operation means it is like here. You can check inductor is storing the energy from inductor current is increasing from I1 to I2 during T on. During off time again it is reaching from I2 to I1 na?
Yes, sir.
So here the thing is, before this cycle inductor current is I1. At the end of this cycle again inductor current is I1.
Yes, sir.
So here, due to this duty cycle, whatever the duty cycle we have discussed here, it is such that during this T on and off time are such that inductor average energy is becoming 0 over one cycle. If you increase the duty cycle, then it will not possible, right? So it is like your operation will be it will not be a steady state operation, right?
Yes, sir. Sir, for, example for the buck converter, the maximum value is 0.5, no, sir.
D max, no, it is not a maximum value. It is a
They're getting maximum 0.5.
0.5 is the value corresponding to your delta IL and delta VCR maximum. It doesn't mean that we cannot keep D greater than 0.5 for buck converter.
Okay. Could you tell that which value we can take the maximum for the duty cycle at a particular value?
That depends on your circuit parameters. Again, I am saying, because while discussing the circuit, what we are doing L and C, we are taking the generalized values. Na? We are taking switching frequency as a EF generalized value. So all these parameters, it depends what will be your maximum value. And for that, how we need to proceed? Suppose, for example, if they ask the question like they have given some switching frequency, value of inductor, value of capacitor, na? Then I need to check whether corresponding to that duty cycle, okay, whether my inductor, just now whatever I told na, during 0 to T1, whether the inductor is storing the same energy, and during T1 to T, inductor is releasing the same energy or not.
Okay, sir.
So for that, I need to, again find these values, that is I1 to I2, I2 to I1. Then and only then it is possible. It is not like that it depends on only one parameter. No, it depends on your L, C, F, etc. Right?
Okay, sir, for a discontinuous conduction, for the charging is taking the time of the T naught. For the discharger, we are taking only for the beta T. Means the charging and discharging both are not equal in that case.
No, charging and discharging both are equal.
But
for discontinuous, you are saying, na?
Hi, sir. But we are not going up to the T.
Yeah, not going up to the T. Right? It is before T only it is discharging.
With that quantity,
but you can check over one cycle, can I say that energy stored by the inductor is equal to energy released by the inductor? Definitely for some short time, that is from beta T to T, IL is 0. Yes or no?
Yes, sir.
But energy stored is equal to energy released, na? Because from 0 to T1, current is increasing from 0 to I2.
Yes, sir.
And from T1 to beta T, it is decreasing to again 0, na?
Yes, sir. Sir, by seeing that waveform, we are saying that up to T on, that energy is storing, from T on to beta is the discharging. That quantity will be equal, no, sir? Whatever we are doing.
No. 0 means you are saying D and D minus beta both are same, right?
Yes, sir.
No, it is not like that, because you can check during 0 to T on, that is during 0 to DT, whether we are having the circuit for 0 to DT and for DT to beta T, whether we are having the same circuit. No, na?
No, sir. Both are different.
Because at one time the switch, for example, consider the boost converter. 0 to DT switch is closed down. When inductor was storing energy, it is like a Vs and inductor only. There only inductor and Vs were in a circuit.
Yes, sir.
And from DT to beta T, what is happening? The V0 will come into the circuit, na?
Yes, sir.
So that's why we cannot say that these two intervals are same, right?
Okay. Yes, sir. I got it, sir. Thank you, sir.
Yes. Yes. Next.
Hello, sir.
Yes, please.
Sir, in boost converter, from, I mean, till the T on time, why is that diode like in the off states?
Why the diode is in off state? Okay, in a boost converter, na?
Yes, sir.
Because the capacitor is releasing the energy. This thing, na?
Sir.
Yes, capacitor is releasing the energy. So when capacitor releasing means discharges, sorry, capacitor discharges. So when capacitor discharges, it is like capacitor current is flowing like this.
Sir.
So this capacitor will try to discharge like this also, but this diode will feel the reverse voltage and it will turn off. Right?
Okay, sir, but the inductor is actually like storing energy, na, sir. So it won't like the current won't flow through the diode.
No, but inductor is storing the energy, but before this circuit, you can check here we are having a short circuit, na?
Yes, sir.
So whether the current will flow, inductor current will flow into this path, or whether it will go through the diode towards the terminal X. The current is having a tendency that it follows the path with lesser opposition.
Yes, sir.
So
Sir,
maximum current will be flowing here only.
but sir, these switches is also something like this MOSFET and things, na, sir. So it will be like in the ideal case, this diode and this switch both will be having like zero resistance path, na,
Okay,
sir.
okay, huh?
So then how can we tell that?
No, but you can compare the overall opposition offered by the switch and overall opposition offered by this circuit. I am saying that is diode and resistor and capacitor, this circuit. You can check, definitely this opposition will be very high compared to that of your switch.
Okay, sir.
So that's why maximum current will definitely flow through this branch, right? And for analysis purpose, we are considering total current is flowing through this branch, right?
Okay, sir. And the capacitor will discharge only through the load.
Capacitor will discharge only through the load. So for that only we connected the capacitor there, na? Suppose if capacitor is not connected, whether during 0 to T on load current will be non-zero or load voltage and load current will be non-zero? No. So that's why we connected a capacitor there, right?
Sir.
Right.
Sir, and could you explain this discontinuous conduction in that how the working of the circuit, like?
Okay. Discontinuous conduction means 0 to dt the same operation. Inductor stores energy, capacitor discharges. Okay.
Okay, sir.
During dt to beta t, that is T on to beta t. Okay. It is like a switch is in an off state, inductor releases energy, capacitor will go on charging, right?
Okay, sir.
But beta t to t, it is like a inductor has released the energy fully now. So that's why your IL will be now 0. The meaning is, as the IL is 0, the meaning is your diode will feel the reverse voltage.
Sir.
Because of this capacitor, because this voltage will be greater than that of compared to that of this voltage. So that's why circuit will be at the rest position.
The capacitor voltage will be greater than the input side voltage.
Yes. Because it is a step up chopper, na, that is a boost converter.
Sir.
Your output voltage is greater than the input voltage.
Yes, sir.
Right. So that's why diode will feel the reverse voltage. Means from beta t to t, diode is in an off state, switch is in an off state, right?
Okay, sir. Sir, but and we cannot tell that this 0 to T on is equal to this beta. I mean, T on to beta T time also.
No, these two are not same.
Okay.
Because you can check during 0 to dt when inductor stores energy, inductor is having only this circuit, na?
Sir. Hello. Hello. Hello, sir.